Good afternoon, everyone. We deliberately started a few minutes late to give a chance for a few more people to come in, and I've seen a few extra people come in, so we're going to get started. If there's anyone out in the hallways there, maybe they can't hear that far. Hello, everyone, again. Thank you for joining us this afternoon for the i3 Project Technology Showcase. My name is Ron Van Holst. I'm Director of Research Development for High Performance Computing at Ontario Centres of Excellence. I'd like to remind you that if you are tweeting today's session, please use the hashtag OCE Discovery. Our first speaker this afternoon will be Alan Lalonde. He is the Senior Executive of IBM's Canada's Research and Development Centre and will be starting us off today by providing an introduction to the i3 project. Alan, over to you.
Afternoon, everybody. Lots of familiar faces, and so hopefully we'll do this a little bit quickly, but give you the information that hopefully you need and want, and serves its purpose well. It's funny that we're sitting in here as I'm speaking to you. My boss is actually sitting on that stage over there, speaking to others as well. So lots of applause, cheers, throwing things in the air. That's all very welcome. As Ron said, my job today is to give you a little bit of an introduction to some of the innovation ecosystem plays that IBM, in conjunction with our collaborators, namely, and very gratefully, the Ontario Centres for Excellence, our university partners, the Government of Ontario, and the Government of Canada, have been putting into place in the province, what we're trying to achieve and how we're trying to leverage the ecosystem to enable an entrepreneurial, not just mindset, but a capability in the province with disruptive technologies. So I'm going to talk to you about two pieces, SOCIP, and as well about IBM's innovation ecosystem play called the Innovation Incubator Initiative. You'll hear it called i3 from time to time as well. But I do want to give you a little bit of context and a little bit of background as to how we are where we are. And it really starts with a challenge that all of us are extremely familiar with. It's a challenge that has been plaguing, I guess to use a dramatic word, Canada, Ontario, and all of us for a number of years, and that is in our ability to innovate. The capacity, the capability, and the outcomes driven by innovation. And no matter which measure you look in terms of measuring our capacity to innovate, whether it is in terms of our labor productivity or our investments in R&D, our capacity for the labor force to actually make a contribution. For a great number of years, Canada has done an extraordinarily good job in terms of academic performance, and I would say a less than stellar job in terms of our capacity to innovate. And if we define innovation not as how people used to think about it in terms of developing new products, inventing new things, developing new services, but rather measuring innovation and defining it by the ability to impact both economically and in terms of applicability, the broader value chain, the broader ecosystem, then we've fallen well behind our G20 competitive countries. And in fact, our startups and our entrepreneurs, many of whom are here today, we've in terms of their performance, been much slower in terms of their ability to actually impact the market. And some of them just frankly disappear. And so a number of years ago, we looked at what were the causes of some of those barriers together with our partners. And this is a very recent perspective from the Canadian Chamber of Commerce on the top 10 barriers in 2015 to competitiveness and innovation. If you looked at the same list of 10 factors and barriers back in 2010, 2011, 2012, when SOCIP, and I'll talk more about SOCIP, was first launched, you'd see that it was much more practical barriers in place then. There were things like the lack of access to high-performance computing, the lack of tools, the lack of skills in terms of digital capability. Some of those things are still there today, but indeed we have progressed, and in part it's because of the kinds of innovation initiatives that have been launched, that have been taking place in the years since 2012. But notably today, these two that I've highlighted are still ones that I think are something that we really need to address as an ecosystem. Firstly, it's the ability to approach innovation as an ecosystem. All parts of it, from academia and government to small and large industry and everybody in between, our ability to innovate must be addressed by looking across the ecosystem and making sure that all of those points, all of those touches, all of those players are equally being addressed as part of that. The second one that I highlighted is clearly this lack of digital skills in the marketplace. Speaking very selfishly from an IBM perspective, our ability to attract, to hire, and to retain the appropriate skills in the marketplace in this new digital economy has been challenging, frankly, over the last many years. And we believe that initiatives like the ones that we're going to talk about are necessary not just to deliver capacity and capability for entrepreneurs, for startups, for large and small enterprises alike, but it's important so that we can actually develop the methods, the capabilities, the projects for people to actually get the skills that they need as well. So these barriers, while still, I guess, improving to some degree, are really still in place. And all of the things that we've been doing since 2010, 2011, really are efforts around trying to improve this capacity to innovate in the province. And so how many in the room might know a little something about SOSIP or have heard of SOSIP? Maybe just a little bit of show of hands. Okay, about half the room. So I will give a little bit of context then. So back in 2010, 2011, a group of people were brought together to talk about some of those barriers to innovation. Again, at that time it was things like access to infrastructure and capacity and digital skills. They were really fundamental or very pragmatic barriers to actually innovation. And so together with 7 major universities, the largest research institutes in Ontario at the time, the Ontario Centres for Excellence, the Province of Ontario, and the Government of Canada, we formed a consortium called SOSIP, the Southern Ontario Smart Computing and Innovation Platform. Just luckily, I happen to have the Executive Director of SOSIP now sitting in the front row here. So you were late, by the way. Yeah, there we go. But let me tell you a little bit more about SOSIP and why we are so very proud of it and why it has formed the opportunities that we are now starting to see for these new initiatives like the incubator initiative that I'm going to talk about. So launched in early 2012, those 7 major research universities together with IBM and OCE came together and looked at how do we fundamentally address those barriers that we talked about. How do we put in place assets, people, capability, resources, training, all of the kinds of capabilities that we needed to address the ecosystem as a whole. The federal government made an investment of $20 million. The provincial government made an investment very similar, nearly $20 million. And IBM provided a $175 million investment to build a capacity to innovate in the province, built on top of 3, at the time, high-performance computing environments. At the time, the fastest supercomputer in Canada, the first and largest dedicated research analytics cloud in the world, and thirdly, the first and only advanced computing platform, agile computing platform, FPGA environment. And what our goal was, across 5 government-declared priority areas of focus, those being health, water, city infrastructure, energy, and advanced computing, was to enable the ecosystem by providing access to those high-performance computing environments, but more than just access to some game-changing, globally leading, highly competitive infrastructure environments. It was to put all the other pieces around there. It was to put in place support and teaming and governance and structure and support for commercialization and pre-commercialization so that we had all of the elements of the innovation ecosystem addressed as part of that. I'll skip ahead very quickly and tell you that some of those assets included indeed that infrastructure was very important. And I know we're going to talk in a moment about the future of high-performance computing, and some of my colleagues and peers are going to talk a little bit about that. That was an important piece of that, make no mistake, to make sure that we had not just a very fast computer capable of doing multiple simulations and very challenging and complex simulations and modeling, but to put in place quite literally the fastest supercomputer in Canada was extremely important. I'll tell you and kind of give you some forward and look back. The good news is that in our second phase, that fastest supercomputer actually is now doubled in size and is still the fastest supercomputer in Canada by, I think, a factor of 2. So those computing platforms, the analytics research cloud, the Agile or the FPGA computing platform are very important as well. But I'd say just as important was that teaming piece, the collaboration of academic leaders, small businesses represented by OCE, large business, not just IBM, but other large enterprise players as well, and focusing on research priorities that were important for the country, important to the province of Ontario, and important for all of us as communities. Additional to the infrastructure and the people, and that includes things like postdoctoral fellows and project executives and all those kinds of capabilities that are necessary, was a focus on skills. Skip ahead, and all of these assets, and I call it the secret sauce of what SOCIP really is, over the last 3 years has more than eclipsed its priorities. When we led into SOCIP, the promise was to execute roughly 30 projects across those 5 research focus areas, using high-performance computing and all the support mechanisms in place. Instead, in the first 3 years, from 2012 to 2015, we executed more than 50 projects. Roughly 75% of those had a small or medium-sized business that was either created or grown substantially because of their engagement in SOCIP. We delivered more than 300 new skilled people to the ecosystem, having the training and the requisite capabilities around big data and analytics. We established more than 240 new jobs out of this initiative, and we established a pipeline, a 10-year pipeline of more than $2 billion worth of forward-looking revenues. But I'll tell you what's not on the slide, and maybe for a future slide, Alyssa, is that it also declared a forward-looking view of $2 billion worth of healthcare savings as well in the province. And so some very strong and big impacts because of what was initially launched in SOCIP just 3 years ago, or 4 years ago, I guess now. I'm going to skip back, though, because since that time, really what we've done is taken a look at those kinds of capabilities and said, how can we do more? In late 2014, early 2015, we approached both the federal and provincial governments and said, here's our scorecard. This is what is working. This is why it's working. What do you think? What do you want us to do? We're happy to continue as is. And a resounding call from all of the stakeholders to expand and increase our scope and capability. And so in 2015, in April of 2015, the federal government provided a further $20 million, matched by $65 million of IBM contributions, to create a second phase of SOCIP. And what we effectively did was add a 4th supercomputing or high-performance computing environment, happened to be a large memory system that is staged at Queen's University to complement the supercomputer at U of T and the data analytics cloud and the FPGA platform at Western. And it allowed us to actually augment our total project capability from roughly 50 to 80 or more projects, thus increasing, obviously, our economic impact and the ability to actually impact the ecosystem in a material way. We also added 4 new focus areas, including digital media, advanced computing, or advanced manufacturing, as well as mining and cybersecurity. 4 things that were identified, both our federal and provincial colleagues, as incredibly important areas of investment for them. And we opened up SOCIP to include far more capabilities and members. And so we're proud now to have more than 15 university and college members that are bringing us new projects every day and allowing us to work with them, to collaborate with them to deliver these kinds of capabilities and impacts. So I would tell you first and foremost that if you are in the habit of supporting SMEs, supporting academic researchers, supporting anybody in the ecosystem, I'd really ask that you spend some time at this conference. I think in booth 1506, as you walk in the main entrance, literally the first booth on the left is the SOCIP booth. And really talk to the folks there about how these kinds of capabilities, the most advanced computing platforms in Canada, the advanced support, technical help and resources to go with that, and the right networking capability can be brought to bear to help the kinds of people that you support every day. So that's a little bit about SOSIP, and I give you some context with that because there was a gaping hole in the story that I just told about the success of SOSIP. Not sure if anybody caught it, some probably did, but I mentioned that the federal government repartnered, if you will, with SOSIP in early 2015 to expand the capacity and capability of SOSIP to deliver more of that network and that ecosystem to everything that was needed. When we asked the provincial government to actually participate in this and look at stretching SOSIP a little bit more, their answer was very interesting. It was, we love it, we want to do more, but we think we can do even more than what SOSIP is doing. And there still exists some natural barriers in the ecosystem that we believe that working with SOSIP and with you, IBM and OCE, we can actually deliver a stronger impact, a broader impact. And so literally from the end of 2014 until early 2015, or to late 2015, we worked on addressing this gap, which I show up here, which is really that an inordinate amount of investment, capability, insight, and expertise gets poured into the R&D cycle of innovation. The ideation, the innovation of new product and ideas, the early development of these capabilities, and bringing these capabilities towards a pre-commercialized state. And we have all kinds of programs, university research programs, government-funded programs to do that. But there was really not a lot of commercialization capability supporting the other side of this ecosystem. And so the government challenged SOSIP, the government of Ontario challenged IBM and OCE to say, could we actually address this gap that existed between what we'll call the collaboration and innovation side, or the R&D side of the ecosystem, and the incubation and commercialization side of that ecosystem. And lo and behold, out of that process was, under the Jobs and Prosperity Fund of the Government of Ontario, came a new program that was, I would say it was iteratively developed as we worked through the program what this might look like. And it became the Strategic Partnerships stream, which allowed us to actually focus energies, resources, and investments on the entire cycle, not just the R&D cycle. If you look at the SPS actually guidelines and the kinds of intents declared by the Ministry of Research and Innovation, the Ministry of Economic Development of Ontario, you'll see things like strategic and technology focused, innovation, but really at the heart of what SPS is, and maybe this is the commercial for what SPS is for the Government of Ontario, it really is about creating an innovation marketplace, where instead of widgets or products or services that the entrepreneur and the SME community creates and goes looking for markets, can we turn that on its head a little bit and create a demand-based innovation ecosystem, where large enterprises, where stakeholders like hospitals, and banks and insurance companies and the community at large identifies their strongest and most necessary innovation needs and matches those needs to the SME and the entrepreneur community. So it was creating a demand-based innovation engine in the province of Ontario. The second piece of that, though, was to really focus that demand-based innovation engine on the capability to deliver disruptive technologies, not just to provide access. In the case of SOSIP, that was access, capacity, and support for high-performance computing. In the case of this innovation initiative, the incubator initiative, it was really around making sure that we provided support for the adoption of disruptive technologies, the adoption of those capabilities to accelerate commercialization, to better position these SMEs and entrepreneurs' products and services for a customer-driven market, if you will. This initiative was launched at the end of February 24th to be exact. It is a $54 million program that brings, combined with SOSIP and I3, more than $350 million of innovation investment in the province of Ontario. The $54 million is in addition to all of the investments made into SOSIP, and it's really a split largely between the Government of Ontario and IBM. And you'll see in a moment in terms of providing programs, services, people, capabilities to really focus on that commercialization and incubation element of the life cycle. It has four big elements to it. First, We really want to focus on the SMEs themselves, the entrepreneurs, and I use the SMEs, I guess, in a larger term, mean not just startups, but also entrepreneurs, new ideas, the kinds of people that we find in campus accelerators, regional innovation centers, in many of the campuses, but also you find an incubator network that is very prolific in Ontario. We want to help them by providing them access to these disruptive technologies they could neither afford nor have the skill to use on their own, to make sure that we help them to demonstrate their products, their capabilities, and their innovations, to accelerate their time to market, to grow and scale their businesses, not just in Ontario, but nationally and internationally as well. The second major element of I3 is ongoing support for the process. Today, one of the key ingredients of process is to provide not just access to technology and support, but to provide postdoctoral fellows, and grad students, and interns to these projects that are based on process. And we wanted to make sure to be able to do more and more of them. In this case, I3 will deliver more than 100 postdoctoral fellow annual instances so that process can deliver to these projects the kind of skill and capability they need to be successful and to actually implement these kinds of disruptive technologies. Thirdly, a strong focus on skills and education and training, and that's not just on campus, although campus curriculum is an important piece of that. It includes curriculum that is focused on engagement and projects and startups, but it also will be baked into and filtered through OCD and all of the training services that OCD actually provides in the entrepreneurial market. And lastly, and probably the biggest piece of what I3 really is a focus on creating a hub-and-spoke innovation infrastructure. And so if you think about process and how game-changing it was that the fastest supercomputer in Canada is now available to a company with 2 or 3 people, think about it now from a commercialization context. And how can we put in the hands of these SMEs and entrepreneurs the right tools and the right capabilities to be game-changing for them as well? And we identified that the best and the right way to do that was through the Ontario Network of Entrepreneurs, the existing incubator and accelerator network that was here, to look at the kinds of services that they delivered and to inject an infrastructure of disruptive technologies and access and capability and support to allow them to be more capable in their efforts as well. This is kind of a real picture of what that means, and it is, if you will, what we'd like to call the innovation marketplace, but that demand-based innovation ecosystem that we've been talking about. On the left-hand side, looking at large enterprise clients, large enterprise partners, the largest of entities, so banks, the insurance companies, the hospitals, pharmaceutical companies, but also clients and partners for all of us out there. And to expose their needs, their opportunities, their insights, their wants, to that broader community of entrepreneurs and ideators that are out there. So that the supply side and the demand side can be brought together through that Ontario network of entrepreneurs and to leverage both sides of the ecosystem. The goal is to deliver this capacity, this capability, this network ability, if you will, across more than 500 small and medium-sized enterprises over the course of the next 2 years. And to underpin that with a technology platform and a governance model that engages large and small enterprise together in that capacity. There's a gamut of programs that I3 will deliver, including additional postdoctoral fellowship programs, again, those implemented by and governed by process, the ability to support true customer demonstration projects. And I'll tell you a little aside that when we met with the Minister of Research and Innovation and the Minister of Economic Development, both of them said, how do we help these small companies not just innovate, not just get the skill and have access, but how do we help them get their first customer? How do we help them grow and give them a place to sell their wares and their tools? And so this idea of bringing real large enterprise and institutionalized need together the entrepreneur community and then creating a true customer demonstration project where the entrepreneur sees the benefit of their first customer directly from the project is a really important piece of it. We'll also establish IBM innovation hubs as well as take space and provide this technology and this infrastructure through all of the 5 major incubators, the 14 regional innovation centers, and the campus-led accelerators as appropriate. And make sure that there's support project data analytics interns, interesting aside, an ability to support these companies as they go international. So the same capabilities that they have in Ontario that they get from their local incubator or accelerator will put them in environments elsewhere in the world, in China and Australia, in South America and Europe, to have the same capabilities available for them there when they go to market there as well. So lots of great programs. I won't go through all of them. There's probably 18 or 20 really key or focal programs with this, but it really is making sure that we're getting into the hands of the entrepreneurs a ready-made customer, a set of disruptive technologies that are game-changing for them, which you're going to hear about later today, that they're getting access to, and they're seeing the future of computing that you're going to see a little bit more of in a minute, and that we're giving them all the support and the capability that they need to be successful and to grow and to scale without that risk of missing a market, missing an opportunity, or not doing it at the right time or in the right place. So with that, I think I'll pass it back to Ron. And if you have any other questions about the IBM Innovation Incubator Initiative or SOCIP, again, right at the front of the entrance hall, there's a number of booths there that there's a lot of people who can help you through your questions, or we'll be around all day. With that, back to Ron.
Thank you for that presentation and a token of thanks for your speaking. All right, thank you very much. I have a short presentation, and I'm going to make it even shorter. And I guess I'm moving through now at this point in time. Alan talked to us a lot about the history of the SOCIP program and how it led through the partnership with IBM and OCE and SOCIP into the i3 program. I'm going to look at the context for that at a much higher level, and then talk a little bit about some of the programs that they'll be rolling out. Again, we had the introduction to SOCIP, and SOCIP I Trust is a program that many of us are familiar with, and if you need to learn more, as we pointed out, we have a booth right by the entrance there. What I'd like to emphasize on this program is it is a program that was designed to help businesses be more competitive through collaborative research projects, providing these advanced research computing technologies in order to accelerate the speed of innovation in partnership between academia and industry. We've seen many, many projects that have leveraged this platform to create many wonderful innovations. And there's the icons of the, I think there's a pointer in here, right? Of the technologies on the side, an open innovation ecosystem where all the contributors to the new technology share in the properties around those technologies, big data and analytics projects, and as is mentioned many times, skills and development training. And what we found that a lot of the projects were commercialization focused, but they were very much pre-commercialization. Partners being IBM, OCE, SOCIP, and now we're counting 14 universities and colleges and growing. By contrast, i3 is an expansion of the same concept. It is more targeted for business growth, helping businesses scale up and accelerate and grow in Ontario. Again, an open ecosystem, much of the same partners as before, focusing on a new array of cloud service technologies, which you'll be hearing more about as the subsequent speakers come forward. Skills and development training, a much tighter focus on commercialization, and what I like to emphasize here, support for adoption of smart computing technologies. Again, one of the barriers to innovation, certainly that as we have seen in many of the research studies in Canada, is Canadian businesses don't adopt technology as quickly as they should in order to innovate. And so some of these programs have been designed to help Ontario businesses adopt innovative technologies more quickly. Again, a very high level view. We had hoped today to discuss more details on the eligibility requirements and intake process for the i3 program. Those are still being negotiated and still being worked on, so please stay tuned. Really reach out to any one of the OCE people that you're already working with. We expect to launch this program in detail very soon. In fact, OCE and SOCIP and IBM are working together to make sure that we design these programs for maximum benefit for companies in Ontario so that they can adopt these technologies and grow their programs. The first one that I want to mention, and I won't try to point all the way over to that screen, is the Customer Demonstration Program. That again is a project designed to help companies demonstrate smart computing technologies. It speaks to what Alan talked about on building on the demand-based innovation. At OCE, we call that procurement innovation. We have had programs at OCE in the health space and in the education space where public procurement engines can be used to drive innovation. This is a adaptation and a growth of that concept into the computing space using our partner IBM and their channels in the marketplace to build demand for the innovations in the Ontario economy. We'll also be featuring a technology adoption internship. So these will help companies seeking to adopt more advanced analytics technologies, leverage the talent in our universities and our engineering and science students, and in fact any students studying data in any discipline to be able to adopt technology at a more rapid pace in support by all of our partners and the skills that will be developed there. More postdoctorate fellowships for the SOCIP program, partnerships with incubators and accelerators. We will be partnering with a select set of incubators in Ontario, as well as the new IBM incubators, to help develop custom services around these other programs so that companies can be accelerated in their growth. Again, we've mentioned as part of the supply chain valuation, IBM will be introducing high potential companies to demand-side innovators who are looking to grow their innovative landscape through innovative companies. IBM will be awarding instances in their cloud services in SoftLayer and Bluemix and Watson, as well for select companies that show potential to drive tremendous economic benefit in Ontario by the integration of those services. And IBM is also contributing access to its global entrepreneurship program. And again, program details and processes are coming very soon. How does this help business? Well, I think one of the key attributes of this program is we are hoping that the programs that are just about ready to roll out will help businesses accelerate in Ontario. Research indicates that the real new jobs in an economy are those jobs created by companies that grow rapidly. So we are in this program together with IBM working to create an ecosystem, to create an environment that allows innovative companies to grow quickly. And it's also enabling these companies to scale their innovations on a scalable platform. That would be the cloud services that are being offered to applicants to the program. The ability, again, to help businesses adopt analytics. Businesses need to be increasingly more competitive today. There's a broad recognition that use of data, effective use of data, and analytics in data is an area where almost all businesses need to do greater adoption, and there'll be considerable support for that. More a traditional value for the SOCIP program is the collaborative R&D. It's risky for businesses to do research, and it's especially risky for small businesses to do research. In this environment, you have the ability for businesses to do collaborative research, de-risking innovation, de-risking research, and bringing your ideas to market that much more quickly. And last but not least, collaboration through innovation. As we work together from different sectors and from academia and industry, large companies and small companies, is the ability for us to accelerate innovation in the marketplace, grow jobs, and grow our economy and make Ontario a prosperous place to work. Last slide, that's my contact information, but again, as I've mentioned, access to these programs, contact any of the people that you're already working with at OCE, and we'd be glad to steer you through the many new programs that will be launched as part of the I3 initiative and get access to the benefits of those programs. At this point in time, we're going to be moving on to some of our technical speakers. I'd like to welcome Brad McCready, Vice President at IBM Power Systems Development and Board Advisor at the OpenPOWER Foundation. Brad will be speaking about enabling technologies to innovate in the big data area with unique high performance and cloud computing platforms. I'll turn the podium now at this time over to Brad.
Thank you. Thanks. All right. This working? We're on? Yeah, there we go. Hi, everybody. How you doing today? I'm going to give you a little talk about what we see going on in the industry with high-performance computing, with computing in general. Let's see here. We're going to use this, I think. Okay. Let's try that. Let's try that. Here we go. So if there's one thing I want you to remember here, there's two trends right now that are driving technology in the industry. And I think these are the two dominant trends. The first one is the fuel that has driven most of computer innovation is rapidly changing. If you look at what goes on in IT and computing today, you see that first curve there on the left there. We could probably do a little bit of this. This curve over here, or this curve over here, that bottom curve, that's the Moore's Law curve. I'm sure everybody's heard the term Moore's Law many times over their life, or if you've been around IT, you've at least heard it. That's the cost performance takedown that computers have been on for about the past 3 decades. You could maybe argue 5 decades. Very rapid, very strong. Enables computer makers like us to keep building computers generation after generation. You keep selling them into your install base, selling to people that have them, and they want to buy them because the next computer is twice as fast, half as expensive. You save, usually you can lay out $1 million for computers to get that return back in computing in less than a year. That's going away, and we'll talk a lot about that, and I'll describe what that trend is like right there. That's starting to flatten out. The second thing that's happening that's very, very strong in the industry that's changing IT and computing is this thing up here called cognitive. There's a bunch of trends, but the cognitive is the most interesting one. We're going to talk about that one too. The cognitive trend's really interesting, is related to the first point. Most computers are sold these days. You walk up to somebody and say, I got this great computer. It's twice as fast and half as expensive as the previous one you got. And they say, great, I'll give you all the money I want for it. Well, I'm not going to give you all the money you want for it. I'll give you, if you could take my computing and IT spend down 10, 20%, I'll give you $1 million for that. If you could take it down 10, 20%. That's usually how computers are sold today, like I told you. With cognitive, it's a much, much different discussion when you sell somebody a computer now. Now you can walk up to somebody and say, you know what? Buy this computer and I'll triple the size of your business. That happens a lot today. That happens a lot today, right? Think of the number of computer companies right now that are founded on, I got a real big, nice big room full of cheap computing. I fill it up with computers, and now they got a business growing. I mean, there's a lot of easy examples of it. Apple. Apple's a great example. Apple got a nice room full of computers that run iTunes. And now everybody's kind of addicted to their cell phones, and they get to sell cell phones at a very, very large profit. But it's really built upon a lot of cheap apps that are running on a room full of cheap computers. Wow. Now somebody's made their company about 6 times as large because they got good IT. Never used to be able to make that argument. 10 years ago, you could walk in and make that argument to a CEO over and over again. Nobody really believed you. Now you can believe it. So we'll talk about that one too. 2 strong trends that are changing computing. Here's the data behind the first trend. I plotted on here Moore's Law coming down, cost performance coming down really, really fast. Every 2 years, you could get another set of computers that are twice as fast as the one you had before and about half as expensive. If you look at this little curve here, Intel, I used an Intel term on here even though I'm from IBM, the tick-tock curve. That curve is that each generation you get a new technology. Each time you see a tick is a new technology node coming out of their fabs. It used to be they came down very, very quickly, and each tick you get a 2x reduction. Now they're starting to flatten out, and that's what you can get just working on processors and semiconductor technology alone. That's the key point. If all you're working on is processors and semiconductor technology, that's what you get, is that curve that is flattening out. All these companies that you think of and you know the name of, Google, Amazon, Facebook, they're built their companies on coming down this curve right here. A room full of cheap computers coming down very, very quickly. This trend right now is a huge inhibitor to the large cloud data centers making the forward progress. Let me give you an example of what it looks like when you see this trend come to an end. If you've been around computing for a long time, you'd be very familiar with this chart. This is a chart that we actually showed the chairman of IBM every year. This one dates back to 2003. I actually pulled this off my laptop. It's a chart that we actually showed the chairman at that time. I think it was Sam. We got to see this one. But this is the plot of frequency, the frequency of a microprocessor. This used to drive the economics of the microprocessor industry. You could go to somebody and say, hey, I got a 1 gigahertz processor. They'd say, great, I'll give you $50 for it. Tell them you got a 2 gigahertz processor, you get $100. Frequency was a measure of economics in the IT industry for quite a while. So this goes back to 2003. Next year, this is actually what this same chart looked like. The same exact chart was like, whoa, everything took a big bend over. This turned out to be right. If you look at the predictions on here with the big black curves, it turns out to be right. Intel, all their microprocessors went up to about 3 gigahertz and parked. IBM's microprocessors went up to about 5 gigahertz. We came down to 4 and we parked. And that's where frequency of microprocessors has been ever since that time. We've been about these same spots. Big discontinuity, just like I showed you on the previous chart. Big discontinuity in the moving forward of technology. Now, that's an interesting chart, and I'm going to try and help you understand what this means. We're going to talk about something everybody understands a little bit better. Airplanes. This is the plot of the same thing for airplanes. So here we got speed of commercial airline travel on the y-axis and time on the x-axis. Now this is a log plot, so I don't know how many scientists we got in here, but this is a log plot. These are the same as those exponentials I just showed you. Here you can see the very first plane, the Wright brothers. Things go up, they get faster and faster and faster. Airplanes are speeding up. Each plane that came out, man, everybody was all excited. Plane comes out, let's see, we got the Curtiss flying boat came out, and it went about 70, 80 miles per hour. And then along came the Ford Tri-Motor, it broke the 100-mile-per-hour barrier. Everybody was real excited. This is cool. We got much faster planes. Everybody's paying more and more for the planes. Then you come along, the Concorde comes along, and it just goes way up there. Super fast plane, doing really good. Now we're flying fast. And then what happened? Anybody want to take a guess what happened after that? All the planes kept getting faster? No? Anybody guess? Every plane was the same speed. So obviously commercial airline travel came to a screeching halt. No more commercial airline travel, right? Well, I flew here this morning, so I guess there's still something going on. They're all the same speed. Huge discontinuity. Everything came to a screeching halt, big change in the industry. So what happened over here? What happened after every plane was the same speed? Not too long ago, I was over there visiting Boeing, who put the 787 out. It's a good example, though, of what happened. 787. Real interesting meeting with Boeing. The most interesting thing about the meeting with Boeing was what? That the 787 is sold out until 2020. Why is it sold out? Because it's a lot faster than all the other planes? What'd they do? What'd they do? What'd they do? What did 787 do? Oh, they went and innovated along a different axis. The 787 is 30% more fuel efficient than every other airplane in the world. And now it's sold out, not because it was faster, but because it's more fuel efficient. That's what happened in airline travel in general. All these planes, they kept making them, kept going, making them what? Made them bigger, more comfortable, safer, easier to use. You know, I was reading one time from Boeing, I was looking at their website. Their whole website is a TCO sales, but how fast they can get everybody off the plane and back on, coming down to how they design the armrests on the plane so grandma's bag doesn't get caught on the armrest as she's walking it down the aisles. But that's the kind of change and the kind of innovation they're doing, innovating along a completely different axis. Here, something else we understand. Everybody understands these. Anybody know what those are? Anybody want to take a guess? Anybody want to guess? No. They build them up here in Canada, guys. Dodge Challenger. Dodge Challenger. This one's built right in Ontario, as a matter of fact. Two cars built, what? They're built, this is a 1970 Dodge Challenger, that's a 2010 Dodge Challenger, 40 years apart. Look at the performance specs on the two cars. Almost identical, 425 horsepower, does a 13-second quarter mile. You can have a lot of fun in those things. It's good. So anyhow, my son graduated. My son turned 16. Gave him my old red F-150 pickup truck. I had to pick between these two cars. I decided I was going to look good in the Dodge Challenger, so I had to pick one. So which one did I pick? Well, the decision came down to this page. Over here we got 425 horsepower and not even a disc brake on the back. No airbags. Don't even get a lap. Didn't even get a shoulder belt. You know, you just got a little lap thing there. You know, so a lot lacking on safety over here. Over here, you got your 2010 Dodge Challenger. Still got 425 horsepower. Still got a 13-second quarter mile. But now you get, you know, some lighted cup holders. That's good. If you're driving along at night, you don't want to spill your whiskey, especially if it's Canadian Club. So anyhow, you got your lighted cup holders. You got your run flat tires, navigation system. So I ended up with the one on the right. We got the one on the right sitting in the driveway. But again, what happened? The whole automotive industry, right? Performance, performance, performance. You couldn't sell this car on the left if it didn't win at the track. Couldn't sell it. Wouldn't even have a shot. Go over here to the right. Innovating along a different axis. I mean, now, you know, it's just the opposite of this car here, right? What's the number one thing that sells a car today? Electric. You know, we got all kinds of electric cars over here, and pretty soon it'll be self-driving, but it's going to be things other than performance. Keep innovating on different axes. You could probably plot the whole automotive industry. Axis change of innovation. Goes from performance, goes to comfort, goes to to electronic gadgets, safety. Safety sold a lot of cars. A lot of airbags, a lot of anti-lock brakes sold a lot of cars. Okay, so what's going on? Let's take this back to the computer industry. Same thing's going on in the computer industry. As you come down this curve, and this thing, you know, the shrinking of the transistor fueled the industry for so long. Now, everything else is starting to fuel the industry. The businesses, the most important businesses in the world are still built upon the cost performance of technology coming down on this curve. But what's new, and the place to innovate is to invent these little green lines of new ways to take cost performance down that isn't driven by a $50 billion fab. Important point. The main things selling in the industry right now in IT are things that bring cost performance down and they don't require a $50 billion fab. As a matter of fact, they're pretty easy to come by. Not that hard to come by them. So if you come down here, right, what's one of the first things? In about 2008, when processors started to flatten out and not getting the cost performance advantage, what was the first thing everybody did? They did virtualization. Take a room full of computers all running at 10, 20% utilization. Just put a little piece of software on there, a hypervisor it's called, and next thing you know, you can run them up at 50, 60% utilization. It's like getting 2, 3, 4, 5x more computing for the same price. You didn't have to buy a new computer. I just got to put a little hypervisor on there. There's a company called VMware that did quite well because they did that first. Well, they didn't do it first. We did it first, but VMware made a fair amount of money doing it. There's a whole series of these. Now, what's the interesting thing? Really important point. What's the second important point about that? That innovation, unlike Moore's Law, where you could keep building new transistors over and over again, once you virtualize, you're done. You can't virtualize again. You know, we've already got virtualization here. We got utilization of the computers running up. So you got to do something else. Well, what was the next thing? A lot of people went to flash technology, using flash drives, solid-state disk drives instead of spinning disk drives. That's another green curve. What else happened? Well, people said, I'll use cloud computing. So instead of having a room full of computers I need lots and lots of admins doing, I'll create a cloud. I'll manage this whole room of computers with just 2, 3 admins. That's another curve down here. But the point is there's a lot of different little green curves out there that need to be innovated that are driving our industry right now, and people are looking very, very actively for them. We're looking very, very actively for them. And that's what all of these are, and there's a lot of capability. The main thing these days that are driving a lot of these green curves is accelerated computing technology, GPUs, FPGAs, attached to processors. After you get through a lot of these, you're down to that technology, and that's what's driving the industry a lot. Okay. Oh, I forgot, I made this chart. I actually bought another Dodge Challenger. After I got the yellow one, I came over here. So this is a real heck of a car here. This is an interesting one. And I decided it was a good analogy for the talk I just gave. So over here we got 425 horsepower, but you know what? People still wanted to go faster. I wanted to go faster. So this is a 707 horsepower car right here. This one does 0 to 60 in about 3.6 seconds. But here's the interesting thing. You can see the trade-off. It can actually burn a gallon of gas in 45 seconds. It's got a supercharger on it. It's an accelerated car, so it's got acceleration technology. Think of it as a GPU or an FPGA. And it can burn through fast. So yeah, you don't get to pass up very many gas stations, but the automotive industry's following the same process, or you could say the computer industry's following the automotive industry. I don't know, you could call it either way you want. But much of the same thing's happening. And lots of more gadgets, right? You got a whole computer in there. You can get your choice of apps. You still got lighted cup holders. I thought that was key. You still don't want to spill anything. And you burn a lot of gas. So I kept the old one because it burns less gas. Okay, back to the first point. I wanted you to see this point. This is the cognitive computing point. So if you go through again, right, remember, the value of computing now is becoming ungated. Used to be computers were valued by how much can I save you on what you're spending already. Now, people will believe you, and computers are actually creating businesses. They're more than just a tool like, you know, a hammer. Like, give me a bigger hammer, I'll pound more nails. Okay, fine. How many nails you got to pound? Here's how big a hammer you need. Now it's like, hey, give me a computer. I can start a new business and make money that I never thought I could make before. That's what cognitive computing can do. You could see this because this is the trend that we've been on the total market, total addressable market. This is a computer that we use in our strategy presentation, total addressable market of computing. This is the trend we've been on for the past 2-3 decades right here, been going right up this slope here. Now, most people agree that with the advent of cognitive computing, that we can actually probably going to drive a lot more business. You know, Walmart or Loblaws, I'll use the Canadian term, Loblaws genuinely believes, right, if you can get enough Twitter feed data, you can get enough weather data, and you can get enough Pinterest data, bring it all together, run analytics on it, they can send ads to the right person to buy the right thing at the right time. People really believe that. And it can be done. It's been demonstrated. You can do push ads on the cell phone and make more money. That's what this exponential growth is right here. That's why people really believe it's there. People really, really believe that if you can go and get, you know, enough of a, you know, research data brought to the right spot into with the right patient data and the right medical history data of millions and millions of people, you can go and cure diseases or give people the right drugs to solve a problem that you couldn't have solved before. People believe that. That's cognitive computing. It has lots and lots of applications, whether it's medical, retail. You can just about name any industry you want, and you can probably make money off of data that people have sitting around when combined with the right data from the modern era, such as Twitter feeds, Pinterest, Facebook, and all those things. And that's what this is showing right here. So that's the second important point. So if you're in my shoes, so what do you do? If you believe what we just said, what do you do? And I noticed that the terms came up quite a bit in the previous 2 talks. What we did is we said, you know what? We're going to do open innovation. That's what we did with, I guess I probably ought to tell you who I am. I lead the power development team for IBM. So we build all of the Unix and large Unix systems, build the Linux systems and the I-series systems. And we're off addressing these markets, trying to help our clients solve these problems. And what we did with our technology is we opened it up. We said, used to be, you know, we would say, okay, we're going to go and build everything you need to go get your job done. Now we said, you know what? We're going to take the technology that we had to build the systems. We're going to let rooms full of people like you or anybody around the world take that technology and let you solve the problems. Because the number of things that we got to do, those little green lines that I told you about, it's so great that you can't do it all yourself. So we're going to create an open ecosystem to do it. So in our terms, we built, whoops, how do I go backwards? In our terms, we took all of our firmware stack and our OS and hypervisor stack. We opened that up. We took the chip technology. We actually opened that up, let people in on that. We actually took all the board and system, the hardware technology, all that, let people build on that. And then we also help the ecosystem build the open software stacks, whether it's to do cognitive, machine learning, deep learning. You pick your favorite workload, databases. We help the whole industry use those open. So we took the whole technology, opened it up. Team will tell you more about that, the talks after me. It's been amazing how fast it's picked up. We opened this up a couple years ago, and now we've got over 200 people, 200 groups, I should say, involved in working and developing on the Power platform. And we're getting solutions that we hadn't even thought about. And you'll see some examples of it. But the whole point is the industry is inventing those green lines at a pretty good clip on the Power platform. This chart I wanted to put up here. It actually was what we use in our investor briefing when my boss briefed the investors at IBM. But it's an important point that I wanted a room full of people like you to know. And the point that I want you to know is equally important to the technical or the technology innovation you come up with is the business model innovation. Equally important to the technology innovation anybody comes up with is the business model innovation. Right now, if you look at most of the companies that are succeeding, growing like crazy, and actually doing some incredible things, they are moving to new business models. It's the same thing we're doing with Power. This business model that I'm describing of opening up the technology is not a business model that we would have come up with 10 years ago. We took the technology, opened it up, and we plan to monetize it in completely new ways, ways that we didn't use to monetize Power technology. But if you also just think around the industry and look around, most of the people that are going really fast are doing it under new business models other than, hey, I invented a really, really cool thing, pay me a lot of money for it. It's usually, hey, I invented a really cool thing, give it away to somebody, and hope to get the money from somewhere else. That's generally what it is, right? Easiest example, Google, right? I invented lots of cool software to go do search. How do they monetize it? Well, they get the money from the advertisers. Lots of examples. Let's see. I like the Apple example again. I keep using iTunes. iTunes, right? I got all this media. I got all your media right here. I'm going to monetize it selling you a piece of hardware. I'll give you iTunes for free. Give you iTunes for free. I'm going to make all the money off the hardware. So lots of examples like that. But you could go on and on. Most of the people right now that are growing fast in the industry are monetizing through ways other than classic business models. So that's an important point. The other thing that we did with Power is we went into and now have lots and lots and lots of connections to other open ecosystems. Interesting way that development's taking place in the industry. But right now we actually have joint relationships with all three of these large other open ecosystems, OpenStack, Linux, Open Compute. And we're all working together to solve various ways and make lower cost computing. And that's the kind of relationships you see building in the industry a lot. And that's an important point because right now most of the innovation that's going the fastest in the industry is an open innovation path. It is very, very hard to be a single innovator, even for a company the size of IBM, and innovate fast enough. So you got to do it through linkages and leveraging lots and lots and lots of these open ecosystems. This chart I just put up here just to get you thinking used to be all of our development was right here. We called them our E and our S series, and that basically says, IBM comes up with the idea, gets the customer requirements, we build it, we sell it. Here now, if you actually look, right now, Power Systems, if you go back as recently as 3 years, all Power Systems in the marketplace came from IBM. Today, now, there's about 60 Power Systems in the marketplace. Still only 3 of them come from IBM. The other 57 come from our partners. And they're all built by our partners. We just recently had an OpenPOWER Summit. That's the name of the open ecosystem. I didn't talk about it. The guys will talk about it. But the open ecosystem we built around Power, called OpenPOWER, we got about 60 of our systems are being built by those guys, by the rest of the industry, and not built by IBM. We enable them, we help them get them built, we help them think of clever things to do, but they go off and do all the building. I'll skip that chart as I'm running out of time. This is kind of an interesting chart. This is kind of the corollary to the chart that I showed, that I talked about earlier. But if you look at these systems right here, each and every one of these systems now that we have, starting with back here in the 2015 timeframe, they're all accelerated computing systems. But if you look at it, all we did was build the processor. The accelerators came from NVIDIA. The high performance and accelerated interconnect comes from Mellanox. And again, that's all a result of us taking the technology, opening it up, and allowing others to attach to it. And then if you go to each generation, you know, we get more and advanced acceleration, and we get highly differentiated solutions out here that you should hear a little bit more about. But that process of creating the open technology back here in 2014 is what enabled this roadmap of accelerated stuff. None of this technology was in Power Systems back in the 2013 timeframe. As a result of this, we got a much, much broader product line. We used to only build products up here and here in the pre-2015 timeframe. Now we got all these products down here. And all of these products down here, you know, especially in the LC line and down here in the other clouds, are all a result of the open innovation that we've enabled the industry to go do. That process of that open innovation is one thing I want to just dwell on a little bit, is we do help our partners a lot. I was just telling some of the guys before we came here, there are many, many small companies and small startups now that the Power development team works with that we go and help. We can provide know-how, we can provide hardware, we can provide lots of things to help a small company get going so that we can get an innovative solution out that we couldn't have otherwise finished ourselves or didn't have the idea to go do. So my last chart that I'll go to hand over before I hand over to everybody else is, you know, we want everybody to engage in this open power community. The technology we have is very, very good, and we're able to share it. We want to share it with people so that we can get solutions that we wouldn't have otherwise come up with to enable us to solve some of the basic problems that the industry is facing in the modern era. So with that, I think I'll stop. I don't know, I've left some time for questions. Does anybody want to ask a question? That might be kind of innovative. No, yeah, we do have a question. Yeah, sure. I'll repeat it so everybody can hear it.
Well, I'll just try and talk into this. So there's two technology trends you haven't talked about that I think historically have been important. One is the number of instructions that you can get per clock cycle. So it's not just how fast the clock goes, it's how much work I can get done. And the other is how effective are multiprocessors, because two chips do twice as much work as one chip. And as we get to 50,000, 100,000 processors.
Yep. So the question was, what about the two main trends that have helped us improve performance over the past 3 decades? And the two trends are parallel processing and more instructions per cycle, or microarchitecture. So both of those are being used very effectively these days. If you actually look at computer microprocessors, and I've led every processor since, basically I've worked since Power 2, so I've been building microprocessors since about 1996, designing the architecture for them and shipping them. We've gone in order. We've gone out of order. We've gone back in order. We've gone out of order again. We've multi-threaded. We've single-threaded. We've branch predicted. We said, no, we'll flush the caches. We've done just about every microarchitectural trick there is to do in the book. I don't think we're going to see a lot of performance improvement out of microarchitecture going forward. I know there's some guys that are sitting down in the Austin labs that would probably clunk me over the head if they heard me say it right now. And maybe some guys in Hillsboro, Oregon at Intel that would say that. But we've done a lot of microarchitectural tricks. We're not going to see a lot of movement from those. Parallel processing, that is essentially what people are doing these days to solve the problems. They're doing it in a very brute force way, meaning they're building big cloud data centers. Google puts out 50,000 computers at a pop into one of their pods, and that's, oh, I'm sorry, you want to do some more search? Okay, fine, I'll get 100,000 computers. Oh, you want to do some more search? I'll get 200,000 computers. The problem is, and Google knows this better than anybody, is while that works, and that's what people are doing, it doesn't bring cost performance down. It's just meets the need. Microarchitectural improvements would bring cost performance down. Going and just slapping more computers in there is what people are doing, but it's not bringing cost performance down. So the guy that's going to win and going to make money is the guy that brings the cost performance down, and that's really, really important. So yeah, I mean, parallel, I would actually say the industry is getting dang good at parallelism, and that's a really important tool. But unfortunately, it doesn't bring that cost performance curve down fast enough. Yeah. Any other quick questions before I hand it back? All right, I'm going to hand it back. Thank you.
Thank you very much,
Yep,
Brad, for a very interesting talk.
Yep.
And a
There you
very
go.
good question to Greg, or very good answer to Greg's question.
Okay, good.
Before I invite up the next speaker, I was very much enjoying his analogies on the fast cars, and maybe maybe Brad might consider in a future version of his presentation something that our keynote speaker said at the opening. J.B. Struble was talking about Tesla. Now I know Tesla has their ludicrous mode, right? And I think it actually goes faster than your 3.6 in 0 to 6. So, anyway, we won't go down that path too far. But it's just interesting that one of the big challenges that Tesla had is onboard computing, and getting a computer inside of a car that's not only energy efficient, but is powerful enough to be able to drive better than a human. So something to think about as we're looking at computing challenges. Our next speaker is actually two speakers. The next two speakers are going to come up together and present together, and I've got to sort of dovetail my notes because I'm going by Friday's version of my script. Our next two speakers are Jonathan Dement, the Program Director of Power Systems and OpenPOWER Innovation at IBM. He will take some time to tell us about how OpenPOWER enables companies to collaborate on and innovate computing technologies leading to unique and advanced systems for cloud computing. And also he'll be joined here on the podium by Michael Paolini. He's Senior Executive of the Office of Innovation. All right, okay. You can correct your titles, and we're going to go with a tag team presentation, and I'll get off my script and let you guys take it away then. Thank you very much. I think you have about 40 minutes. And we're a little bit behind schedule, so if you come in 5 minutes early, you'll help everyone.
Right.
So.
Yeah, our goal was to bat cleanup because we didn't know how long Brad was going to go, and neither one of us wanted to be the one going after him, so we're now both going after him, because, you know. So I'm actually a senior technology staff member working in corporate headquarters on strategy, and
Jonathan,
that's the
I work for Brad here, so I get to get graded here by the boss. So I helped put together these systems, and I was going to focus. He gave you a good high-level view of the strategy, and I was going to go through some examples here of how we've kind of taken that strategy, work with some startups, put together some innovative technology and some solutions, and kind of give you some examples to get your thought process going in that respect.
Right. So to kind of kick it off, I guess, can you hear me all right? I'm cutting in and out, and I apologize for that. I wanted to bring the strategy thought into this, right? The market is changing in a couple of ways he highlighted, the first of which is the transistors. We've kind of been at the same power envelope for a long time. You're allowed to use a certain amount of watts. After that, you have to start cooling it exotically. And the performance for those watts has been kind of stagnant for a while in the terms of frequency. So if you think about it, the road to performance in the future is using those transistors more efficiently. And that's usually a specialization or a tweaking, the innovation that we were talking about. And given that CPUs are general purpose jack of all trades, you really want them to continue doing that for the legacy software, but you want to pair them with innovative processing, the parallel processing of a GPU or of an FPGA or of an ASIC or what have you. And so as we start to look at ways of innovating, we're really looking at the trend of massive data that's in motion that you can't store. We're looking at the trend of the business being able to afford it, the trend of the transistors, and how to specialize the processors and improve performance for an overall lower TCO. And when we start to think about moving the data, I want to come back to that, the most expensive thing you can do is to move data from one place to another. And if you think about a central processing unit, you're moving it from the network into the memory, into the central processing, then back out the other way. It's much more efficient to process that where you find it, at the network, at the hard drive, at the memory, and when necessary, centrally. And so in order to innovate and move the systems forward, we had to create this thing called OpenPOWER, where we start to open up our pipes, the memory pipes, the I/O pipes, the connections to the CPU, and allow accelerators to be full citizens. And so really what you're kind of seeing is us reacting to the sharing economy that's occurring, to the data anchors that are starting to occur, and to the physical limits of the fab as well as the financial limits of the companies. Right? And so that kind of rolls us into a nutshell for you of why we're doing the OpenPOWER. And so the OpenPOWER really is a strategy of collaboration. And we're borrowing the thoughts of open software, of the Apache Foundation, for example, and how do you apply that to hardware? How do you apply that to a full system? And we have both models, one of which is full participation, collaboration, fully open, but we also have the option of monetizing that, of making it someplace that you can harvest money from. And we're not going to restrict the business model. We're going to allow you to pick and choose and blend it. And so that's the other aspect of OpenPOWER that I want to call out is business model innovation. Okay. We have about 11 working groups today inside of OpenPOWER. A few of them have come on very recently. As personalized medicine is one I will call out. As recently as halfway through 2015. This one has the most academics and universities in it. It's also the one we're most excited about. What I'd say is come innovate at the top level if you don't find yourself at the chip level, at the bus level, at the memory level, at the hard drive or network level. It's open to all levels because we need a lot of innovation to keep the pipeline going of performance to tackle the enormous data and things that were coming down. In terms of groups, one of the things I want to call out is that we have about 50 universities up at the top. Unfortunately, none of these universities are Canadian yet, and that's one of the reasons why I'm here. This is kind of a call to arms. I've been coming up here since, 2010 when we started SOSIP, and I've grown very, very fond of this region. And I would personally ask you, for selfish reasons, to make me come up here more. Please come join us, be part of this. We can use you and your innovation. I'm going to turn this over to Jonathan to talk about the history and some of the achievements, because seeing is believing.
Yeah, I think so. We've had this kind of incredible run with OpenPOWER, and I hope it's a success. We will copy now into like a bunch of startups and further innovation. But from the point we first started this, just seems like a decade ago, but it was only a few years ago. We started with Google. Brad mentioned Google a number of times. We mentioned Google and started with NVIDIA and Mellanox and Tyan, and got together and said, hey, how do we open this up? How do we create this innovative marketplace, for ideas instead of a closed ecosystem controlled by one company? We need, hundreds of companies innovating, and we've been through this progression. And what's cool is you'll see, I won't read through all of these different achievements here, but what you're going to see is kind of going from, an idea to suddenly now actually winning two of the largest supercomputing deals in the world, right? I'll talk about those a little bit more in a minute, but we won those with the U.S. government and then with the United Kingdom government, and of course we built big computers here. And you're seeing this trend in the government side, right? Who also needs open computing, right? If you think about it, there's no worse thing for a government to be tied into a single architecture, right? They don't want one company succeeding. They want hundreds, thousands of companies succeeding. So the governments quickly realized, we don't need a monopoly in our data centers. We need open innovation and collaboration. So they put their money where their mouth was, and they invested. And then we saw, the hyperscale data centers coming next, right? And of course, Google was part of it from the beginning, but Google has kind of this history of not being very vocal about what they're doing inside of their data center, kind of famously secretive about it, which is why we tagged in our little announcement there at the bottom, which is really significant to us, was that this is one of the first times they really publicly stood up and talked about something new they were doing in their data center. We're actually mentioning real things they had done, porting work they had done, applications they were deploying, things like that, right? So that was very significant, and announced a partnership with Rackspace, which surprised me. This was cool. I think when Rackspace started with us, there was no idea that they would end up doing a server design in collaboration with Google. Right, and when we announced this, Rackspace stock went up like 6.6% or something, right, on the news, and that was cool to see. It's like we helped make that connection, and that's something that's exciting to me now that I get to do daily in my job with these 200 member part companies, and universities and stuff is make these connections. Sometimes I think I just need to stop trying to think of good ideas myself and just get out of the way, right? And just all I need to do is make introductions, right? Because I can pick up the phone now and talk to heads of R&D across, really across the world. You'll see on another chart here, worldwide. And that's an exciting ability in working with university guys, small companies and such. We'll show you some examples of that in a minute of making these connections and saying, okay, Google, you have a problem. How do we help? So, Brad described that problem in detail, right? Their problem, so it happens, if you solve that problem, you'll make quite a fortune doing it, right? But there are others, right? How do you solve the problems for all of these other hyperscaler customers? And now we're really starting to move, from governments to hyperscaler, and now the biggest trend is starting to see is really this commercial enterprise space, right? Our class, and this is where we grew up and we know and love this space. Banks, retailers, hospitals, these kind of people that are now sort of kind of taking those trends out of the hyperscalers and seeing, hey, we want that too, right? We want massive accelerated computing. How do we do that, right? We're not as sophisticated as a Google, right? To do that, but IBM, we trust you. This OpenPOWER ecosystem, innovators come in and play with us here in the commercial and enterprise segment, and that's where we really see this thing, go gangbusters next.
Right.
So, go ahead,
So
Mike.
with respect to the government, I wanted to point out that we have 3 of them on here, right? I don't know how to make the laser pointer go. Hopefully, wrong button. The Chinese government has officially endorsed OpenPOWER as its official, right? Yeah. And that's in addition to the UK spending 300 and something million pounds, and the U.S. government spending 300 and something million dollars on Coral. And I realize that you guys may not get visibility to that, but that combined with Rackspace and Google, hopefully it's getting your attention that there's a lot of movement underneath the water from the tip of this iceberg. And it may not be facing you because you don't see the logo on your desktop every day, but it's certainly there. There place. You were right.
Oh yeah. Also, so yeah, this couple of things you see on the show. One, we want to note this is a worldwide thing, right? Yeah. So please don't think this is just happening. We talk a lot about things that are close to home, but we are working with universities, with research centers all across the world, right? But as Mike noted early in the presentation, what's notably missing here is we need a few bubbles there in Canada. And I would like, I think SOSIP is a fantastic start. And so we want to, I'm up here too, I'm from Austin, Texas, right? Making the trip to come and try to find some partnerships here with small companies and with SOSIP affiliated things and see if we can't use that as a sort of catalyst point to get, OpenPOWER things going here. The good news is you already have infrastructure. You have servers. I learned today you'll have like 18 of these servers or something in the SOSIP program. Yep. With FPGAs. We're going to put GPUs and all that kind of stuff in there. So you will have the infrastructure. So now we need to go, do the next round, which is really the fun part, which is cultivating the ideas and building that up. But we got to get some. That's next time I'm here. It'll be less than a year. Next time I'm here, let's make sure we have some bubbles from Canada locally.
All right. With respect to cloud computing, we've started to distribute it around the globe in order to give you guys access. And as you'll see, there's 2 locations in North America, one in Oregon and one in Texas. There's some locations in Bombay, India, in the Czech Republic, also in China and in Brazil. And hopefully, with your help and demand, Canada soon. It's a question mark there because we've got to make sure that you guys, in fact, want to participate here. So once again, that call to arms, I'd love to have that as a feather in the cap. With respect to the clouds, I want to talk about an announcement we had, which was SuperVessel. And SuperVessel is a collaboration between us and NVIDIA and Xilinx. And it's basically a cloud system, a power system that has also enabled onto it accelerators, the NVIDIA accelerators, the Xilinx FPGA accelerators. And it is free to use, and it throws into 3 zones. One is an enterprise zone for businesses, one is a zone for academic research, and one is a zone for individuals. And so we can accommodate kind of all sizes there. And the software comes with it. In particular, the announcement that I would make is from April, which is the Xilinx software for the FPGAs, the high-level synthesis tools, which you usually pay the arm and a leg for, are now free to use with the SuperVessel. And so you could log in from your desktop at a coffee shop and compile and push these things up, writing in C, in C++, and OpenCL to push it out to a GPU, to push it out to an FPGA. In particular, this one, Xilinx being the FPGA. And so that's very, very exciting for me because, again, it's not one size fits all in computing. Strong threads are very important for serial programs, but parallelization is equally important for streaming and things where you're doing the same task over and over. And having 100,000 cores applied to something in the form of a GPU or an FPGA is a lot more efficient by orders of magnitude watts than, say, 24 cores, which is what a CPU is. All right, you've already seen this chart, lots of ways to engage on this. So now we're going to hand it on over to Jonathan to finish out the hardware side of this.
Press that green one?
Yeah.
Okay. Yeah, and I promised to show you some technical examples, right? So I want to go through a few of those. At first, it'll be a little, I like to point and stuff, so I'll just have to kind of, I guess I have a laser here. I can do it this way or half of you here or there. But I'll talk to some of the things on this page. And Brad mentioned, a lot of work going on here at how do you innovate around chips and components, right? How do you open up the processor and the buses to that processor such that people can build co-processing technology, right? We've mentioned several times, it's GPUs, it's FPGAs, it's ASICs and things like that, but it's also more, right? If you look, one of the things that Brad mentioned that, what's happening in the microprocessor industry, if you think about it for a minute, you realize the same problem's happening to DRAM, right? The memory industry is going through the same issue, right? A $50 billion fab just doesn't do it anymore for memory either. And so these guys are having to figure out new models of memory. And so now you're hearing things like 3D XPoint, you're hearing about MRAMs, you're hearing about all kinds of new persistent memory technologies. And we realize that's a really powerful and disruptive force, right? Maybe that's the lighted cup holder of the microprocessors. And so we've embraced that. We've grabbed onto that, and we built a board. A little. Oops, sorry, I hit the wrong button there. Let me go back. We built a board here that we've kind of offered up to research folks. It's got an FPGA on it, but it allows you to connect in these new types of memory, right? So you can plug in a MRAM or a 3D XPoint or whatever you can get in a DRAM form factor, and there's an FPGA sitting in front of it, and now you can start to experiment with the programming model of that, right? Very interesting programming model being on the memory bus. So as Mike was saying earlier, the data's in memory, right? So what if we can bring the compute off the processor and to where it sits in memory? It's a very powerful concept, right? It's tricky. It's very difficult to do it there, but you can do it there in certain aspects. Not in all, right? You can't interrupt. There's other restrictions that are odd, but you can start to play with that programming model and see, can I take some of these high performance compute aspects, right? Can I do floating multiply adds sitting right there in front of the memory,
Can
right?
you turn the memory, right?
Right, and so it never even comes into the processor cache, right? Stays out in memory, and the calculation is moved to where the memory is, and it's processed there locally and stored back in memory. Very, very innovative idea, right? And we're playing with a lot of research and folks on that. We've also, we've moved up. You'll see a lot of announcements coming around our components and systems, right? So you'll see cards go. When we had the OpenPOWER Summit a few weeks ago with GTC out there at NVIDIA's conference, we pulled the hardware table up of showing, we have this kind of tradition every year of showing all these hardware innovations on stage. And I think the first year we had like 20 of these things. Well, this time I laughed because they literally had a table that was like the length of this convention center, right? To try to show you all of the different hardware innovations that were up on stage. Brad mentioned 60 servers, right? There were also something like 30 different accelerator cards, right? With an FPGA or a GPU or some new memory thing or something, right? That there was a huge array of these things, right? And I only knew about, half of them, and I felt I had somehow failed in my job that I only was actually aware of half of this. But at the same time, it was powerful to see, hey, I'm really glad all this innovation is happening, and I'm learning about it. And you can see, people then building systems and building and all these things. So now the combinations are huge. Right now, I have new FPGA cards, new GPUs. You hear about the NVLink capability of our systems, and I'll show you a little more about that in a second. You have these new memory things. So now, okay, great. I've got the recipe. I got the ingredients to a wonderful new soup, right? But I still got to go make something, right? I got to pick something and make it. And that's where this is where I think the action is going on today. At the bottom of this chart, is building solutions. Right now, this is where we pick a vertical market, a problem in the market, right? A client, that has an issue, right? If I go to, as Brad mentioned, one of the world's largest retailers, they're talking to us. The bank's talking to us. A hospital system, I'm talking to a hospital system about genomics, right? And I'll show you a little example of that in a minute. Where they're saying, hey, look, I want to sequence every patient that walks into my hospital. I would like to have their genetic information that would guide their complete care through my hospital, right? Just, and you say, great, sounds easy, right? Well, just storing that patient data is like, a exabyte level problem for 1 year's worth of hospital data, right? It's massive, the amount of data that a single human genome generates, plus the associated metadata and all the processing. And oh, by the way, just in case you get sued for malpractice, you better keep the history of everything you did and all of this kind of thing. So it's a phenomenally disruptive capability to healthcare, but a huge IT challenge is how do I do it, right? Well, I think some of the answers to how do you do that are sitting here on this page, right? And trust me, this page is just a small sampling, right? But okay, now how do I innovate in the storage subsystem? How do I take advantage of persistent memory models and things like this that can solve that problem instead of in days, as we see it takes now to run that human sequence? How can I do it in 30 minutes, right? And we've actually having a real example of that we're doing with the company. So I'll show you some of these. First, just a quick little kind of background. It is important to note, and a lot of people ask about the ARM ecosystem. So we love ARM. They're great. Another ecosystem where they're innovating, and you want to see that, right? You want plenty of innovation and different ideas here. On the other hand, they come from, it's hard to make a cell phone chip into a server, right? It's just at the end of the day, that's a difficult thing. We're taking a mainframe chip and making it into and bringing it down into the space of okay, now it's in a price performance compute perspective, right? Kind of a quick flyby on that point, but you get the idea. But we have a ton of performance to offer in the processor itself, and that's a unique advantage coming from a power angle, right? We have 4 times as many threads. We have 4 times the memory bandwidth, right? We have 4 times the cache in our processor. So that's a huge starting point advantage from a performance. It's kind of from maybe I'll use Brad's point of view. It's like it's much easier to go after these data center problems with his Dodge Challenger than it is to take a Hyundai and try to make it go 600 miles an hour or something, right? So we're starting from an advantage of a high performance processor, and that helps.
Architected for big data, right? And that's the main thing, is that we've had this history of big data, and we've widened the buses, and the performance differences that you're seeing here are because of that memory bandwidth. When you compare it to an Intel processor, you're going to see huge memory bandwidth. When you look at the NVIDIA, you're going to see huge memory bandwidth. Data is the problem, and we recognize that. So your starting place is a very strong serial traditional processor.
Right, and now we have to connect that with these big buses and with these new innovative connections off of our processor to the best of the parallel processing world, right? And that's where it really comes together. When you can put the world's best serial computation processor next to the world's greatest parallel processors, right? However you want to build it, GPUIs or FPGAs or any of these technologies, when you put those two together, you have a hell of a machine, right? And that's able to solve some of these problems at order of magnitude improvements that we couldn't do before. I mentioned this before, but this very concept is what won our big awards with the US governments and with the UK governments. So maybe the good point about here is it's nice when you have big deals that are hundreds of millions of dollars that you can be sure that this technology is around here for multiple generations, right? We're well positioned. We have huge wins behind us, and now we have to stop worrying about are the lights on, right? That's well taken care of. Now it's the opportunity zone. Now it's really how do we go spread this into the small and medium enterprises, things like that, as we were talking before. So one of these differentiating features that we've done that we're really excited about, that's leading. You look over here, these guys doing the self-driving cars and stuff, right? What's one of the limitations they have? They're doing all this work on the GPU. That's great. They've got 6,000 CUDA cores to try to recognize stop signs and cars driving past you and all this kind of thing. That's a hell of a lot of computational power, but suddenly they run into the fact that, wait, you still have to talk to a serial core at some point, right? You still have to make decisions. You still have to branch, and you have to make it. You can do tons of work in parallel, but at some point you still have to decide what you're doing. Are you do you need to slow down? Do you need to back up? These kinds of things, right? And they're limited now by the pipe between these. Oh, I hit the wrong button again. I'm gonna figure that out. They're limited by this pipe, this PCIe pipe between the GPU and the CPU. They're limited by the programming model because these are separate memory spaces. So you suddenly, as a programmer, hit this huge bottleneck where you're dealing with, wait a second, where's my data? Is it on the processor or is it on the GPU? I got to copy it back and forth. Those copies are inefficient. I got this tiny little soda straw connecting, huge RAMs, right? And I can't get data across them. And so, the HPC world has kind of gotten dominated by this idea of thinking, oh, just build more flops, right? Give me lots of GPUs, more flops, more flops. People have gone and built literally like a petaflop system in a rack with GPUs. It's a terrible system. Don't buy one, because they haven't connected it to the bytes that feed those flops, right? So what happens there is you build a petaflop of computing power that sits there 80% idle, which is a huge waste of power. It's a disastrous consequence. But sadly, I see a lot of people buying these computers, right? And this is an issue I think that the industry will quickly figure out and pivot, and we're pivoting ahead of that. And one of the key ways to do that is to feed it, bytes per flop. If there's one metric for you HPC guys that I could scream up and down and jump up and down on, is don't measure your computers by just flops alone. Measure them at least at bytes per flop, and even better, look at workloads, right? Look at what they can actually do. How does this perform on a molecular dynamics problem? How does it perform on a quantum chemistry problem, right? Not, can I run LinPack, right? LinPack is pretty boring at the end of the day. So, I encourage you to look at this. So,
to kind of bring it back to cars, you don't want to drive a 700 horsepower Dodge on a dirt road that's 1 lane wide, right? You'd really prefer to have a very flat, very well paved bandwidth to enable that speed.
There you go. Dirt roads connecting buildings, and this is superhighways, right? Maybe a local appreciated issue here in Toronto, given the traffic I've noticed. Okay, so the next thing I want to show you a little bit from a techie side, right? We recently announced we finally took the covers off our Power 9 processor, right? And you'll see a lot of these themes that we've been talking about. And this is an area, I think, particularly with research and academics, that we're excited to start engaging with people on now, right? Because we've now gone and built superhighways off this processor. That's what the bottom part of this picture is all about when you look at it. And really, I could almost, I don't want to spend very little time telling you, as Brad mentioned, about the microarchitecture of those cores, right? There's more of them, great. You got 24 of them, fantastic, right? What are you going to do with 24 cores? I hope you'll figure it out. But the challenge now is really about where the data resides, which is over here, right? The data resides in memory, it resides on storage, it resides in the network, right? That's where, where's your huge genome sequence sitting? It's sitting on, maybe a spinning disk or a piece of flash or something like this, right? Now the trick is to get the computation to it. Sometimes you'll have to bring it in, but that's where we're building out this model. And you can see we're putting our money where our mouth is there, right? We'll be the first to have this PCIe Gen 4 interface, right? We're excited about that. We'll be the only ones putting this 25 gigabit NVLink connection off our processor, and we're also opening that up for NVIDIA GPU folks. We're opening that up to be an open accelerator bus that we're going to let the industry collaborate. So you can build your chip to talk to our open accelerator NVLink-like bus there, sitting off the same 25 gigabit fabric, and the SMP fabric and all those things. So you can see, this is a tremendous amount of connectivity that we're building off of our future processor precisely for this reason, is how do we connect in all the data. And you can see, there's the details there below on all that. And what does this result in, right? So again, going back to just the processor itself, right? If I start, I used to get really proud about this chart. I used to get really excited. Hey, look, on some really important new workloads, machine learning, SQL, graph, these are all well-known. You guys know these problems. These are all huge opportunities. And I get all excited and say, hey, I benchmarked our Power 8 processor across all these different workloads and compared it to an Intel CPU. And I won't, benchmarks, we can go on and on, but just to get that, I would have said, oh, hey, I'm 1.7x better. That's great, right? I'm going to sell a lot of computers. Maybe, right? Maybe. But really, this is almost the boring stuff now, right? The really interesting stuff is to get to where you're 2x, 4x, 5x, 10x, right? Where now, as Brad was kind of alluding to before, this opens up whole new business models, whole new types of things that we can come in and talk to a CEO about how we can change their business. Not just, okay, how do I reduce your IT budget 10% year over year for the next 5 years, right? This chart might have helped for that, but I'm actually pushing more to the accelerator side. But it's good to know that you have that capability. So one example here, and I'll try to do this one kind of quickly, but we built a system, we call it CAPI attached flash. And CAPI for us is just a way to build coherency across the PCIe bus. We're the first to do it. It was proposed in the PCIe specs, but they didn't, so we said, hey, we'll fix that for you. And so we built a coherent attached flash system. And what this did, by leveraging that coherence, what we were able to do, we were able to get rid of 20,000 lines of code in the kernel that accesses the file system, right? Stuff that was written in the days of spinning Rust, and now going directly to flash, we know can be far more efficient than accessing things directly off a disk, right? A lot of stuff was put in there for reliability and overheads of disks when you had eons of time before that disk access came back, milliseconds, right? Now you're down to microseconds in the flash world. And so suddenly this overhead is costing you lots of computation time to address it, and it's costing you lots of latency as you go through these long path links. So we said, hey, how can we work around that? So we grabbed a couple of OpenPOWER partners, right? We worked with Redis, we worked with Nalitech, we worked with Ubuntu, a number of these guys to put together this flash system where we said, hey, we're going to take this coherent concept on the power processor, we're going to add an FPGA that talks to that link, and we're going to put a bunch of flash behind it. In this case, 56 terabytes of flash. And
I don't think the number's on there, but we went from 100,000 IOPS per second to 1 million IOPS per second, and we did it using 1 core instead of using 12 cores. And you know, the net of that is by reducing the software stack and putting it into hardware, because we had the same memory space. We didn't have to pin the memory, translate the memory, move it across, unpin the memory.
so, yeah, and this chart didn't come through right, so something converted wrong. But what you'll see is, so 2 key things that happen, actually really 3, but 2 key things, just hook up this flash through a conventional mechanism and now hook it up through this FPGA connected method. And we were able to get 5 times more of the IOPS per hardware third. So that's important, right? You pay for a lot of flash. The worst thing that can happen to you is the guy who owns a computer and you buy a bunch of flash, is now the computer spends all its time talking to flash, right? Instead of doing actual work, it's just doing the overhead of accessing that flash. So we fixed that problem. And then we lowered the latency by half. And that's obvious, right? Now my data gets back twice as fast. And that's key importance. The other thing we did that's kind of hard to see here is we reduced jitter. So we reduced we improved the determinism of accessing that data, which, by the way, funny, you think, oh, that's a small little point you make there. Why is that an important point? Banks, right? Financial trading. Well, it turns out every time you get that little jitter, right, that moment where, oops, I crossed a page boundary, and that access that was supposed to take me a couple microseconds actually ended up taking a couple milliseconds. Uh-oh, I just lost a huge trade. And it cost me millions of dollars, right? And so we work with some of these guys that, have too much money, quite frankly, but have a lot of money that would pay almost anything to get rid of that jitter. And we almost accidentally solved that in this case, right? Didn't even think about it until they saw it, right? And actually it was one of our OpenPOWER partners that said, hey, you know what? A bank's been asking me about, could we fix this problem? Turns out we could, and that was a really cool opportunity for us, right? So it's kind of, this process of discovery is fun sometimes. The other pitch line of that is we're able to take what's usually a rack full of Intel servers, and we can actually treat this thing, you can think of it as really fast disk, really fast flash, or you can think of this as slow memory. And in this case, we looked at it as slow memory, and we said, hey, it's slow memory, but it beats a network cable, right? It beats the latencies across of a network. And so we're able to actually take a system that really the only reason they were scaling more servers into it was to add more memory. And then the network label was adding so much latency, or the network cable ruined that memory in effect by adding so much latency to it. Well, by consolidating that back to one box and building a huge bunch of flash at a very low latency, we're able to give you the same effect of the system where it looked like you have a 56 terabyte memory system and get this actually better performance than what you got in a rack of x86 servers. And you talk about an easy deal to close, right? If you're doing this particular application, I can come in and say, hey, what took you a rack of servers to do yesterday takes you, 1 computer and 1 flash array to do now, right? Huge, this is 24 times, or the cost of that flash isn't cheap, so the cost of that's a 3x price production, right? Still 3x is important in a price performance point of view, but a 24x consolidation of systems, right? That's a big advantage. Couple of, this chart I'll do quickly just to say, I had, there's other things here, a lot of different workloads we're showing on here. I've had the opportunity to go innovate on a few. I need a lot more. This is where the startups and the academic guys, really, I'm looking for help here. There's a ton of areas like oil and gas, right? RTM, reverse time migration. And sorry, these are a lot of acronyms, but some of you may recognize them, right? We start with a 2.5 to 1 advantage running this workload on a power processor, right? Again, not good enough for me, right? 2.5 is good. I probably can go convince a few oil and gas companies once they have some money again. I can convince them to come buy my system on that fact alone. But if you really want to impress them, you want to do something big, very disruptive, come in and show them how you can do 10x with the GPU on top of it, right? And so, these are the areas where I want to take the natural strengths of our platform, take some of these technologies, put them together, and really go another level, right? And completely disrupt oil and gas type, time migration, right? The Stack A2, that's a financial simulation, that's risk. You look at the markets now, they're starting to regulate risk and starting to tell these banks and companies that, hey, you have to do this level of risk analysis on your portfolio, right? And what they're asking and demanding the regulators is a computationally unsolvable problem right now at a price that they could do, right? And so huge opportunity. I'll skip this chart. I want to do at least one small company example. I'll keep it to one. This is one I've had fun working with, right? Little small company called GPUDB. They started out of Virginia. They're now in San Francisco. And these guys took a radical concept and said, what if I could not just accelerate a database in a GPU? What if I built the database in a GPU, right? I wrote the entire thing on a CUDA core, started from that concept, right? And then flipped on its head, right? So I'll use a processor here and there for utility I need its memory, so I got to access memory functions. I got to do logging. I got to do some, conventional processing steps. But the heart and soul of this thing, the SQL, queries, the database operations, 100% on the GPU, right? Really cool stuff. And I mean, literally, when you go into clients, you actually have to downgrade the performance because they don't believe you, right? If you go in and you say, I can actually ingest a Twitter feed 1,000 times faster than you can do it on a conventional Intel CPU, they don't believe you. You actually have to come in and say, I can do it 5 times faster, and they get really excited, right? And you just say, just do the trial with me, and you'll see, right? Then when they get the results, they're like, wait, there's some mistake. Something's weird here, right? There's no way you could process this much data, and that's been a real, this we've taken, we're working with huge retailers. You can imagine like all kinds of problems you can solve here, where these guys can say, hey, I can take the entire Twitter hose in. I can take the entire RFID tag database you've got for your worldwide inventory. I can take the entire weather information for the world, and I can put it all together and do analytics in real time and tell you where you're losing billions of dollars in supply chain, right, inefficiencies. I can do that. Before, when they were thinking to do that, they'd have to spend $1 billion.
To questions.
Yeah.
Right?
Yeah. Sorry.
He's going to talk forever on his enthusiasm.
Sorry. Yeah. No, this is my last chart. So I'll wrap up
I'm
there.
monitoring the time here to get you guys out in time for drinks, and I hope you don't mind. But the rest
Sure.
of the time, let's turn it over to kind of questions.
Sure.
Just to kind of wrap it up.
Yeah.
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 All right, so to repeat the question, we've got all this hardware evolving at a very quick rate. What hope does the academic researcher have to develop tools and keep up with it? And I would say, come join the OpenPOWER group, become part of the work group, become part of the input, and help us solve that problem, right? I'm not pretending we have the answers. What I have instead is a giant Lego box that everyone can play with. Think about what you could bring to the industry if you had access to the chip, the firmware, the buses, the memory. If you could put computing anywhere you wanted and still be able to handle interrupts as a full citizen, right? Or if you could collaborate with industry partners. That's what we're offering, is collaborating at SOCIP, collaborating at the startup level, collaborating at the OpenPOWER level. We want to make you aware that the world has changed. It's not changed in places that you're seeing it at your desktop. It's changed behind the scenes, and we're begging you to come help us.
Yeah, let me add to that for a second, just because I want to say, I think one of the great ways to fix is to get specific and to solve a particular problem, and then that dizzying array of 100 things shrinks down to like just a few, and it's actually much easier to go grab the people involved with those projects and say, hey, how do I bootstrap this, right? And we're really good at that. So, Jeff Cassidy here at the University of Toronto is doing a photodynamic light therapy problem, right? He's using an FPGA. He's got a Monte Carlo simulation that he needs to do of photons entering a cancer cell and scattering about, right? It needs to model that problem. And okay, now we can talk, okay, what's the best FPGA card for you? What's the best way to hook that into the system? What's the software you need, the building blocks that you can have that get you jump started so that you're not spending all your time writing, DMA transfer engines. We got that problem solved, right? You can focus in on how do I do this actual Monte Carlo simulation, right? And work on that piece while we'll help you, bridge all the little components that have to make it work at a system level.
Yeah,
So
don't boil the
usually
ocean. Focus on a specific fish.
Yeah.
And OpenCL. So the question is, where's Fortran in this?
Yes. Yeah. So first of all, Fortran runs great on the old conventional CPU, and will continue to do so. So you don't have to abandon the Fortran codes, and those are good clients. I do see, what's interesting now is you do have a shift going on to new programming models, right? OpenMP, OpenCL, OpenACC, and even we've got a few partner companies. There's a cool one, writes a language called SequenceL that's kind of a straight drop-in for Fortran, called Texas Multicore Technologies. And you see that, I think, that bridging those traditional programming models over to these parallel architectures is a challenging problem. But one, I think, we're going through a sea change on that, right? I mean, kids coming out of college today are programming in, Python and Go and they're not writing Fortran. So, there is kind of this necessary shift, but at the same time, we're trying to preserve that over. So that's a fun problem to work on, by the way. You talk about a cool academic project. I would love to work with somebody on, hey, how do we take, a million lines of Fortran code and not rewrite it? How do we convert it, though, to something that's now, performs as well, but then takes us into the future?
The summary is that legacy code probably remains on legacy things for a while. These new architectures, you ought to go to the new programming until we catch up. This is 18 months or less, right, compared to 40 or 50 years of Fortran. We'll get there. OpenMP is next on the hit list, and then after that, but 18 months. Think about what you've accomplished in 18 months as a researcher. Any other questions?
Question.
All right, let's go drink, or whatever you're going to do.
Yeah, it looks like they're serving at the bar. All right, thank you guys. Appreciate it.
All right, thank you very much. Thank you. Well, thank you, Michael, and Brad. Brad was before. Thank you to those speakers. We're getting down to our final speakers. We're going to have a bit of change in gears here. We've got under the hood of the hardware and IBM's open ecosystem. Now we're going to hear a little bit more about their software ecosystem. So our next speaker here, and I've lost track of my notes here, Chris Mallon. Our next presentation is called Building in the Cloud with Bluemix. I'd now like to introduce Chris Mallon, Software Business Executive for IBM Cloud Software. Chris will be presenting IBM's cloud computing platform Bluemix, which is a wealth of services and cloud-based application development. Please welcome Chris to the platform. Has someone walked away with the clicker? Oh, you have it. Good. Good.
Good evening. Almost. Good afternoon. Hey! The industry theater is pumped up. You know why we're pumped up? Because we're going to talk about bread ideas and making money. Anyone out there got a bread idea and want to make some money? Well, get in here. There we go. There we go. All right, as indicated, my name is Chris Mallon. I lead our sales and technical professionals in our IBM Cloud division for Canada. And so, unlike our previous speakers, I have the pleasure of understanding IBM Canada's responsibility and contribution to the overall development and participation in the different ecosystems that exist in Canada. If we look at IBM's contribution to the capabilities in the marketplace and what we can do in the spirit of innovation and what the discovery session can offer you to engage with different manufacturers and vendors and academia, we should be very proud as Canadians. I'm a very proud Canadian, and the ancillary is a proud Canadian who works at IBM. And the reason is because 1,500 kilometers away from here, in a small town called Fredericton, New Brunswick, which also happens to be where I did my basic officer training for the Canadian Forces, but outside of that is the IBM Center of Excellence for digital security. Hundreds of IBM Canada employees live in the beautiful community of Fredericton, New Brunswick, and build industry-leading global capabilities in security. 650 kilometers away from where we are right now, down the 401 into Quebec, does all of our chip manufacturing, not all of it, sorry, a significant amount of our chip manufacturing production happens there. Thousands of Canadians create and manufacture and distribute the technologies that the preceding gentleman talked to you about, and how those are ingested, how those open communities, which we can be participant in as Canadians, can translate into an offering into the marketplace that can help change the world. 35 kilometers directly north up here, there are thousands of IBMers who manufacture IBM Bluemix, which we're going to talk about, database products, and formerly known as middleware or WebSphere capabilities, just up the street, thousands of us. 400 kilometers northeast in Ottawa is a center of analytics at IBM. The foundational elements of our AI efforts into the marketplace are manufactured in Ottawa. So we've got a lot to be proud of as IBM Canada. So when you think about your opportunity to contribute, to participate in our ecosystems, to be an IBMer, to help create some of these remarkable capabilities, we don't have to move anywhere. So with that in mind, I'm going to talk to you about something. The product leader, just as it happens, the gentleman, colleague of ours, who is a fundamental driver behind the IBM Bluemix platform, lives in the suburbs of Toronto. A gentleman named Sal Vella, research, developer, product leader. He is the person shaping this outcome that we're bringing to the market. So, in the spirit of, let me ask a question. Who here, and I hope to see every hand, who here in the past 2 weeks has had a bright idea? Come on, you're very critical of yourselves. Bright ideas, how to translate a bright idea into a capability. The power of the platform and the opportunity available to you to capitalize on, take your bright idea and translate it into money. Back to my opening comments where I was trying to draw attention to us. How do we make money? How do we take that bright idea and how do we translate it into innovation, translate it into the marketplace, and be able to realize the vision that you had of it? A quote here from one of the founders of Galvanize. 2 guys in Starbucks now have access to the same computing power as a Fortune 500 company. The barrier of entry, the barrier to entry rather, of getting into technology, service capabilities, and delivery is diminishing. You no longer need $1 million, 20 people, and 8 months to create something to bring it to the market, because of the technologies and the way they're consolidating, the way they're commoditizing, and how we're able to assemble them and provide a platform for your bright idea. And there's 2 fundamental reasons. One is cloud computing, and cloud computing represents the distribution of compute capability, the opportunity gained to distribute compute capability through the very liberal availability of broadband. The pipes are getting bigger. The technology that delivers data is more effective and more efficient. And as a result of that, we can get more through the pipes. And when you get more through the pipes, you get access to more power. And you get access to more power, we commoditize that delivery. And when that's commoditizing, it brings down the costs. And when it brings down the costs, it makes it more available. And as a result of that, represents an opportunity to get access. So in order to be creative, to exercise your innovation, you no longer have to become an employee of IBM Canada or any large corporation to be able to get access to the resources to create. Those resources are available to you as an entrepreneur. Next, microservices as marketable products. You no longer need 20 people, $1 million, and 8 months to create something. And then once you've come to the end of that 8-month journey and spent that $1 million and delivered to the market, and then realize actually it missed the market,
No one really wants what we created. It was a wonderful idea, but unfortunately, it didn't land. You no longer have that risk. The investments are iterative. Agile is the expression we're using as of late. And so with that, you've got the opportunity to create capabilities and services which contribute to the platform. So the API economy is actually a much broader, and everything begins with data. Our chair, Ginny Rometty, 2 years ago, I don't know if this was her quote, but it was the first time the quote was offered that I had heard it, so I'm going to give it to her. But she said that data is the new natural resource. Think about it. As long as we're around, it will continue to exist. Innovation will continue to perpetuate. But at its core, it's data. And you don't have to own all the data. You just need access to the data. You need to be able to reach it. You need to be able to leverage it, transform it, and employ it to create value and enrich your bright idea. And then in the middle, we have APIs. APIs connect data. They're no more intelligent than that. Well, some of them are a little bit richer, but fundamentally, APIs just connect this source of data with this source of data, this system of record, this system of engagement, to knit it all together to create value between the core data and that endpoint, which is the application on the end. The application is inert. The application on your phone is largely unintelligent. It conducts transactions. It uses buttons that you wrote and conducts transactions from this endpoint back through the data. And the supply chain is the API. So now, recognizing that, things are happening. It wouldn't be an IBM presentation if I didn't stand before you and tell you how we are going to solve world hunger, we're going to solve the oil crisis, and we're going to, and everything's going to be great once we're done. We have the scale, and we embark upon bold capabilities and endeavor to reach those markets and to affect an outcome which is greater than an individual idea, because we have the scale. And you can see the examples of some of the fundamental changes that are happening in the marketplace, whether it be manufacturing. 3D printers have crossed the chasm away from a funny, clever idea into something meaningful that changes manufacturing. Automobiles. The automobile industry is being rebuilt around the whole context of obviously the availability of renewable energies, but beyond that, the integration of technology. That's changing distribution, it's changing our demands. And then ultimately energy. Even the people who are the most emboldened people in the context of fossil fuels are seeing the light and the ultimate future. And every single one of those innovations that's affecting a fundamental traditional industry is being empowered by technology. Every single corporation, every single public sector organization, every single academic institution relies on technology to run, period. No longer do trading floors get away with paper trades. Everything must be transacted. And then we get into the other extremes. We talk about some of the new compute models that exist, such as blockchain technology, et cetera, and what those can mean to the industry changes that are ahead of us, which is the context that says those communications, those transactions are no longer the domain of the institutions. They're now public transactions. Supply chains, financial systems are all fundamentally changing. So it's exciting to be a participant in this. And your bright idea can germinate with the availability of a platform to support the evolution of these technologies and how they're affecting business and industry. So you're an entrepreneur. And by the way, I'm an entrepreneur. We're all entrepreneurs. I currently have a badge that says I work at a corporation that makes stuff. But we're all entrepreneurs because we all have a bright idea. We all have the opportunity. We see something. We can solve a problem. We can achieve an outcome. And we want to see it foster and grow. And we've got the natural resource of data. APIs is our supply chain. And ultimately, the application is the endpoint, the interface that engages the people we want to affect. And then you've got the innovation. So you take an entrepreneur with a bright idea, and you give them the tools and the capabilities. You lower the barrier to entry. So therefore, they no longer have to create something. They no longer need $1 million, 8 months, and 20 people. And they can create something iteratively. And therefore, you can achieve innovation. So in the spirit of the Discovery program, this represents an opportunity for every single one of the vendors and manufacturers out there, for all the entrepreneurs who are looking to create. This represents a true platform to accomplish that, and that's the IBM Bluemix platform. Historically, the barrier to entry on doing anything, $1 million, 8 months, 20 people. Everything that's in the darker color on the left-hand side was the responsibility of you. And everything that is a bluish tone is the responsibility of me. So, as a manufacturer and provider of the service. So on the left-hand side, if you wanted to build, run, manage your own stuff, you'd be buying networking. You'd contact a third-party organization, provide network capabilities. You would have your own storage, your own servers, decide on which virtualization technology you wanted to invest in. Pick an OS, lather on some middleware to make it all connect and talk to each other, and you build the whole stack yourself. $1 million, 8 months, maybe 12 months, because the project slips, and 20 people. We have capabilities in infrastructure as a service, platform as a service, and then ultimately software as a service. Software as a service is typically a very specific business function that we provide. But the platform for innovation is there in the middle. And that's where, in the lighter blue, I can do on your behalf the networking, the storage, the servers, the virtualization. And if your application, your innovation demands of it, you can be customized with your OS, your middleware, your runtimes, your data sources, and what code and what languages used, et cetera. Or you can go to the right, which is Bluemix. And Bluemix is a semblance of capabilities that gives you the opportunity for me to take care of all the stuff that's commoditizing and unimportant. All those advanced technologies that the preceding gentleman shared with you, I have them. They run in my data center. It's in Barrie, in Canada. That technology is available to you. That power is available to you. And I can mitigate a bunch of the unnecessary noise to deliver you the value, which is a platform for innovation, to create on. You bring your data, you choose your code, and you have the opportunity to create and innovate products. So again, here's the stack. You can build the infrastructure. It gives you agility. I want to figure a different virtualization technology. I want my bare metal capability, which is a capability only IBM brings to market in the infrastructure as a service capabilities. It gives you access to power. Why take all the wonderful technology and research and development that's created in those Power 8 platforms, and why obfuscate it with virtualization technology that impedes its capability, impairs it? You can run, if you have high processing demands, you can run right on bare metal, only with IBM. Go over to the right. We're not just a platform as a service. Again, platform service is great, gives you agility. Let's mitigate some of the unnecessary decisions that need to be rendered. What operating system, et cetera. All that matters is the application, the APIs, and the data. We already talked about the supply chain. That's all that matters. What the operating system is, et cetera, the middleware, less interesting. That's not a competitive advantage. Doesn't make your application run faster. Doesn't give you a platform to create any more rapidly. However, you go to the right. And this is where you get to create. This is where it gets exciting for you. So you got the agility. You can run HPC. I can run it right on bare metal for you. You can move up the stack, and I can bring together all the different components to make sure that it runs soundly. Transactions are complete. They execute effectively. It's secure end-to-end, all those demands that we'll have. But then you go over to the right. Let's talk about now creation. Mobile applications, Internet of Things, cognitive capabilities, analytics, flexible deployment techniques based on geography, based on functionality, opportunity to be able to participate in the API economy and reach new business models. All available to you because I took away all the noise. I gave you access real time to rapidly build an environment, choose whatever languages, whatever middleware you see fit, employ them, and be able to deploy and build your applications rapidly. And that represents the opportunity for innovation, to create those applications. Now, just up the street, actually haven't Google mapped it, but it's, we have what we call the Bluemix Garage. The Bluemix Garage is a think tank. It's an opportunity for you to come, whether you be an individual entrepreneur, whether you be a corporation looking to innovate more rapidly, or whether you be part of the academic environment. You have the opportunity with your friends and colleagues to help and engage with us. And we're going to walk you through design thinking. Stickies all over the place. Redesign, rethink how we do things around personas, empathy maps, scenarios, ideation, etc., and overcome all those things. Again, Python, JBoss, all the different predisposed ideas we have around certain technologies that we enjoy or don't enjoy. Those questions are answered very rapidly with a couple clicks of the mouse. Choose whatever you want. Choose it in our platform and our system, and get into the business of actually creating and taking your idea, and turning it and running it on a digital platform to engage with new ecosystems in the API economy. So we have the IBM Bluemix Digital Innovation Platform. And each one of these is not, these icons around the core platform here, is not the end. It's not a thing. It's not a single service. It's actually behind each one of these icons is probably about 20 to 30 services. Now you think, okay, IBM, you're a manufacturer, you built a bunch of stuff, but I don't know if the stuff you built is for me. Here's the cool part. I didn't build all this stuff. I built some of it. I built, towards the top right around the, I guess we'll call it the 1 p.m. time zone, or 1 o'clock, API management. I built my API management technology on there and put it on there as a service for you. We've also got other API capabilities there. Wearable fitness, Internet of Things. We have a variety of services, cognitive and the like, that are built for you by us. But there's also people just like you who went onto our platform, built out a service, and it's up and running. And within 90 days, they have the opportunity of having set up their service and created it, they have the opportunity to transact that service. They have the opportunity to execute APIs, to be able to get their 0.25 of a cent for every API call. So if they create a service which is really cool and gets momentum, and as other entities are creating their services and assembling all these APIs, every single time your API is called, you make money. You want to make money, and there's a platform to do it. You didn't have to buy the networking, didn't have to buy the operating system, didn't have to buy the hardware, didn't have to do any of that. And you were able to capitalize on the platform and the community that we've created. So we've got a bunch of fundamental ones: cloud integration, workflow, the ability to manage and create those workflows throughout the process, predictive modeling, be able to manage and handle large volumes of data. So there's some pretty cool things, mobile applications and the like. And many people have platforms. Many manufacturers in the industry do. But on our next presenter is going to share with you the secret sauce that IBM is, and that's around our Watson technologies. We have, if memory serves me, I think we're up to 28 Watson API services. The opportunity for, to use the current industry term of AI, to be able to engage, create a platform, and you can have the intelligence of Watson AI or APIs to do natural language translation, personality insights, to be able to do sentiment analysis. One of the easiest services we can show is sentiment analysis here. You can go in and build up an application and you can run sentiment analysis. I think it's a 5 to 8 minute exercise, but it's the clever one everyone likes to see, because I'll type in your school name, your corporation's name, and it'll go out and it'll hit a variety of different sources out there, social media sources, et cetera, and it'll tell the social sentiment of what it is that you just typed in. ABC company, McMaster University, whatever it is, and you'll get a sense of the sentiment that's out there in the internet, in social media. And that's a great example of a very simple and clever thing, but we can score you and help you shape it. So you built that really cool thing, that one clever thing, that great idea, and you built it, and you used push services for mobile capabilities. You've used DevOps to be able to rapidly iterate and build and improve and enhance and constantly change and adjust it. Maybe it's an Internet of Things disposition that you're reaching. You're engaging with a machine type interface. And you've got the opportunity to do sentiment analysis so that when you go to create or update or improve that application, that API that you've created, using legitimate sentiment to help you shape what you create and how you improve it. All within one cohesive platform. Again, remove the barrier to entry. The opportunity to create, whether you be an entrepreneur looking to make money, or whether you be an innovator, or whether you be someone in research, someone in academia, a platform available to you to mitigate all the barriers to entry. You no longer need $1 million, 8 months, and 20 people to make it happen. It's all available to you now. And so it's the IBM Bluemix platform which represents that point of entry to be able to reach all that high compute capability, all those advanced analytics, and to be able to enrich your idea and help bring it to the market. And let's talk about that market. That market can be my market, the IBM marketplace. You can participate in the IBM marketplace today. You can do it right now. A couple of you guys are on your phones right now. Go. You can go in right now, log in, and you can get access to the IBM marketplace. And within the IBM marketplace, you can host and monetize your API services. You can take that bright idea and you can formalize it. You can turn it into an offering and a capability in the IBM marketplace. So therefore, someone in Austin, someone in Singapore, someone in Melbourne, when they're creating their clever idea and they're trying to bring it to market, they may very well invoke your API. And they may very well invoke your service to enrich their capability. And every time that your API is called, they're giving you money. And that's a platform that's global, represents the unique isms of Canada as far as privacy and security is concerned because of our distribution of our data centers, and gives you the opportunity to create and innovate in a whole different way a new business model. With that, my name is Chris Mallon, and that is IBM Bluemix. Are there any questions? That was so good, Chris, that we don't need any questions, right? However, I'm going to pump up our next presenter, Watson, right? 2012, Jeopardy, right? It's kind of a big deal for us. You know who Watson is? Hopefully I'm not stealing your thunder, Charles. You know who Watson is? Why Watson has Watson's name? Watson was the founder of IBM over 100 years ago. And his son championed us, Watson Jr., championed IBM into the computing era. And so as a result of that, and our patronage to our history, the creation of this remarkable technology in Watson, we championed it with the name of Watson because it represents for us, in at least my estimation, the future of our compute and our capabilities. And I'm very fortunate as the provider of the Bluemix capability to the Canadian marketplace. I'm very fortunate to have now 20-something services from Watson just on Bluemix alone, all available to you to be able to use and invoke and realize those capabilities. So with that, turn back over to Ron and get on.
Thank you very much, Chris.
Thank you.
There's your token of appreciation for speaking. And for introducing the next speaker for me, that's Charles Quincy, Business Development Manager in IBM's Watson ecosystem, to give his presentation on cognitive computing with Watson, IBM's technology that understands questions and responds with valuable answers in a natural language. So I'll hand it over to our final speaker, Charles, and then there will be our reception. And I appreciate those who have stayed for the whole time. We've saved the best to last. We get to hear about Watson now. Charles.
Thanks. Thank you. Let me get my bearings about me a little bit here. So thanks everyone. I'm Charles Quincy, based out of New York City, within the Watson Group. And what I want to do today is just kind of peel back some of the covers on what Watson is. Chris did a great job of kind of teeing it up. But Watson really represents a new phase in computing. This notion of cognitive, or the synonym of it, artificial intelligence. But let's start with a little bit of history. So computers were originally inceptioned for mathematicians by mathematicians, essentially take abstract mathematical concepts, turn them into code that can then be compiled into ones and zeros that give us a model of something that should happen. And the beginnings of that process and that discovery was really about automation, right? Let's automate credit card transactions. Let's automate getting seats on an airplane, things like that. But no, so this is a great quote from George Dixon writing on about Alan Turing, which of course, if you're not familiar with the Turing test, very big hot topic in artificial intelligence related to having a computer system mimic the functions and perspectives of a human being so that an end user would not know they're interacting with a computer system. No one imagined the extent to which the symbolic logic that had been preserved of mathematicians would unleash the powers of coded sequences upon the world. So we had this huge explosion of the ability to process complex ideas and complex sequences using computers and translating it down to ones and zeros. And at the same time, with the advent of all these things happening, we had a huge explosion of data that was happening simultaneously as a result of our ability to manipulate mathematics in the open world, to create automation. So we've had this huge explosion of data, right? But it wasn't just enterprise data. It wasn't just tabular data, ones and zeros, measurements, et cetera, et cetera. But we started having images. We started having text, people writing things online, videos, all sorts of different things. And there was this hypothesis out there that if these data sources existed and we could marry them with our structured data information, could we glean insights that are deeper, richer, and have context to our end users? Well, this is why cognitive has come about. How do we understand a problem space that cannot be modeled precisely? Every time you swipe a credit card or tap a credit card, that transaction happens the same way every time. And you want it to happen that way. But if you want to understand context, how am I feeling? What's my emotional state when I call in to change my password in a call center? Or what's my emotional state when I'm buying this good or being sold? That takes not a precise model, right? It takes context. It takes an understanding of environment, of conditions, of the individual. So what cognitive systems became was a set of observations of the world that make choices based on those observations, are evaluated based on those choices, and then learn from feedback. And that learning mechanism has become a very hot topic in the discussion of artificial intelligence, machine learning, and the like, simply because the notion that a system can learn seems like a very unique human characteristic, right? But it's really just adding data points to a regression model. It's adding more data points to improve the performance of that model so that way I can get a better understanding. It's not going to be 100%, but I get a better understanding of what's going on. So these systems, I referenced regression models, those kinds of things, they're probabilistic. There's ambiguity in the problems that you're doing and the choices that you're making. These things are adaptive. The criteria may change over time, so context may change, data may change. They're multidimensional. So many different observations are required from a lot of different points, right? You can't have all of your points in the world exist in one data set and create a model of that. You'll overfit it. And your new data points may not fit that model, so you got to think about it in a creative way that at least gets a good generalization of the data set you're working with. And then they have to be interactive. They need to be a set of data points that may change and that may be actually unknown or not well defined. So this is what's kind of defining what cognitive has come to be. So if we created kind of two pillars of cognitive computing, what we're really taking a look at is the concept of machine learning, which is an application of statistics and predictive analytics that allows us to model imprecise problems. And then sensory processing, giving us that context related to the outside world, the world that we are existing in. So, where did this whole thing start? And Chris kind of alluded to it with our Jeopardy showcase that we did with Watson. What we started with is, let's build a system that can take a question, break out its component parts, search through a treasure trove of data that has the answer in it, create hypotheses, merge these things together, and spit back an answer. And in the case of Jeopardy, that answer is in the form of a question. Right, so let's solve this problem. This is a known problem in computer science called the open domain question and answering problem. And I will be the first one to tell you here that we have not solved that problem. General AI is not here yet. There are a lot of people trying to solve this problem. And we understood this is a very hard problem. It is very data set specific, it's domain specific, it's user specific. There are a lot of variables. So how do you break apart what we've learned in question and answering into meaningful tools and technologies that will start getting you to insights and answers in data sets that you wouldn't have normally been able to interrogate? So we broke apart these services in these 5 areas. Question analysis, it's an NLP problem. What is being asked? What's the intent? Can I measure that intent? Can I relate that intent to a specific action? Can I extract the parts of speech associated with that question and then get a better understanding of what's going on so that I can then go search and come up with candidate answers? Natural language processing, of course, is a big component of what I just described. And machine learning really tells the system these are the right hypotheses. These are the hypotheses that you should weight higher. These are the hypotheses you should weight lower. But this takes a lot of human interaction in training the system and being able to understand it. But it's still a set of techniques that, if applied in different areas, can be very powerful. So for example, our speech-to-text service is built on a set of neural networks that is a derivative of machine learning. And neural networks are actually were pioneered, invented here in Toronto, University of Toronto. So, how do I understand the data and how do I understand what are right hypotheses and not? Once I've done that, how do I merge my candidate answers into one set of a list or whatever my end user wants and begin to present those in a meaningful way that the end user will understand and trust? So there's a big trust component here. So when you think about ranking technologies and you think about these kinds of things, you either want them expert annotated, you want them to come back with some sort of confidence interval, right? Because the decision is not on the system. The decision is still on the end user, the person that is using the system to create an answer or to drive an insight. So we built out question and answer, and we built it out in this huge big thing that we did on Jeopardy, and then we broke it apart. And we created these candidate kind of services that we tested and hardened and actually applied different topics and different things in machine learning, in sensory processing, so that they were super performant for the task that they were trying to solve. Right, so let's take, for example, natural language classifier, right? I want to take a string of text and I want to classify that text and tie it to either a response or to an action in my application. There are things in that type of process that you need to have the right models for. If you're measuring intent, you want to have the right vector representation for every word, for every letter. What do you expect to become next? And you want to come back with a score that marries it to the right response. So that's an example. We kind of picked the best models to do that and power that service underneath the covers. So you get a sense of the technology that we're using underneath the covers here in kind of this light gray, and then what the future looks like. But this is a lot, right? As a developer, as someone who's using these as tools to get at insights in text, audio, and video, you may not know the orchestration layer, you may not know which ones to hand off, and those kinds of things. So this is a kind of a chart that was put together maybe 6 months ago. What we're doing now in Watson Group is rationalizing these. So if you wanted to do a natural language processing task, right, and you wanted to identify keywords, you wanted to identify concepts, and you wanted to do sentiment on a set of news articles that you identified as having meaning or signals that may be relevant to the use case you're trying to solve, as a developer, the experience that you want is to have that invoked in a single call where you're turning on, turning off parameters. So what we're doing now within Watson Group and with these services is rationalizing them into their end states. Because it's when you get to a number of APIs, orchestration becomes a difficult component. So this is what we're trying to accomplish now from a technology standpoint and usability. Because what we've discovered is that we've seen with these types of capabilities 4 core types of use cases, problems that are being solved. And these are broad-based by design. But you can see here you have 4: engagement, discovery, exploration, and decision. So engagement. This has been a super hot topic of late related to things like bots, conversational assistants. How do I engage with an end user in a way that's natural, kind of getting at that Turing test? How do I deliver information in a meaningful way that's conversational, understand state? and build those things out. The next is discovery. So we've been seeing a lot of discovery use cases in very text-heavy or image-heavy type of industries. So there are signals and patterns within that that may indicate new discoveries, new research, things like that. So if I could discover within the research that this particular protein is going to become in vogue, and I'm a drug manufacturer investigating that protein, I want to be able to pull back all the research related to that and maybe do a horizon scan of that kind of thing. Or maybe I want to just explore my data. What's in there? What am I missing? What are the components? And then decision. How do I bring back a set of things based on my data set that are ranked in a meaningful way by experts that understand the nuances of the domain I'm in and that can present me with decisions? So I'm going to show you a quick video. Do we have audio? Yes.
Eli, grab it.
This is an application of some of those things.
Eli, grab it.
I'm confused. Which of the 4 things do you mean?
So this is what...
Eli, what color is the object on the left?
It's blue.
Eli, grab it.
So there's engagement here, right? The researcher is reinforcing learning of a robot in order to accomplish a task. And we'll break it apart at the end of the video.
Eli, grab that object. Eli, grab the white thing.
Do you mean this one?
No, the other one. Eli, grab the green thing.
Sorry, that's too big for me.
Eli, what is the object on the left?
I don't know.
Eli, that object is aspirin.
Okay. Is it aspirin?
Eli, this object is Advil.
Okay. That is an Advil.
Eli, how many Advil do you see?
I see 2.
Eli, poke the thing in the middle.
I don't know how to poke something.
Eli, point at it. Eli, extend your hand. Eli, retract your hand. Eli, that is how you poke something.
Okay. Now I know how to poke something.
Eli, poke the red object.
So you see there, right, there's a lot of little subtasks that are going on that the robot needs to understand. And this is kind of a cool application of some of the research that we're doing within IBM related to some of these cognitive technologies, right? In order to interact with the system, you've got to be able to speak to it, right? It's a speech-to-text problem. I need to process the action in that text as a robot in order to accomplish an action. I need to teach the thing that certain words mean certain actions, and then correlate those with movements in the arm. And I need to be able to do that and teach dynamically related to that. So you start seeing the little building blocks that have to come around to actually get a robot to do something that's performative, that performs in that way. And I hope this gives you a sense of, this is pretty state-of-the-art stuff. This is research related technologies. It's hard to train these systems. You have to explain every single little thing to them. But once they get a good model of it, they can perform these things. But we're still a long ways from having autonomous robots running around telling us about all sorts of different topics, right? So there's an appreciation there for how advanced the technology has gotten, but also for where we are. And we're seeing these technologies applied in all sorts of different places, right? We've got robotics, which I showed you, entertainment, banking, agriculture, marketing, telecommunications, all sorts of different places. And all of these companies up here are doing something related to cognitive in a way. but it's not in the kind of way that, you know, should scare you, should keep you up at night, those kinds of things. It is really a set of techniques to either engage users with data in a natural way or to find signals and patterns in data that'll help us to answer new and intriguing questions. So if we, you know, go through some of these examples, right, you have WellTalk that's doing corporate wellness. How do I ensure that I know what wellness programs are available to me as part of my company, what I'm going to get compensated for doing those wellness programs, what type of wellness programs are meaningful based on certain conditions that I may have. And then you look at something like Cognitoys. How do I interact with school children? How do I train a system to interact with language models that are receptive to little kids, right? And training the system to sit on just a little toy dinosaur that'll make kids laugh, but at the same time teach them something. Completely different domains, different contexts, but still the same core technologies that are running underneath. So I leave you with this. The Watson technologies are available for you to play around with. They're on Bluemix. You can go test them out, kick them around. The documentation is great if you're a developer. And we have a lot of code, a lot of recipes out there that will help you build some of these engagement applications, decision applications, and things like that. And keep in mind, these are developer tools designed to help you get insights and create interactions within your applications. So, thank you very much. I know I'm the last speaker before you get cocktails and dinner. So it's not an envious position to be in. But if you have any questions, happy to take some because I have a couple minutes here. Nope. Everyone's thirsty. No. Thank you very much. Appreciate it, and have a great rest of your evening.
Thank you very much, Charles. Very interesting talk. There's our token of our appreciation and your badge back, so you can enjoy those drinks.
Yeah, appreciate it.
And that brings us to a close of our time here in the Industry Showcase. Go and enjoy the rest of the conference and the reception. Thank you very much.